Hi, this is Ryan Eisert again, here for Clemson University's Electrical and Computer Engineering Department. Today we're going to talk about assembly language programming, ECE 273, and specifically we're going to go into Lab 4, addressing modes. Well, at this point you might ask, what is an addressing mode? Well, an addressing mode is actually something that we've been doing all along throughout the semester. It's just how we get the data for a given assembly instruction. So let's take the addition instruction for example. Whenever you want to add something, in any programming language, you typically want to add two things, and then save a result, right? Well, in assembly, we learned that we do that through the add instruction, add, and then the instruction suffix L for 32-bit data sizes. And each parameter, the source and the destination, supplies a piece of data that is to be added. Now, we've learned that we can supply that data using either registers or through the use of constants, or we can also supply the data using memory variables. Now we have to be careful to not reference more than one main memory location at once in the instruction when the data is fetched, but we can use a combination of those three different ways to get the data for the instruction. Those three ways are known as addressing modes in general. It's how the data is addressed to be used within the instruction. Now, addressing modes don't just apply to the addition instruction. You can naturally see how this concept extends to subtraction, multiplication, division. It also extends to the simple move instruction, where you want to move data from one place to another. In order to move data, you first must supply information about where the data is that you want to move. From what we've discussed, we can supply the data to be moved either as a constant with a $sign in front. We could also use a register, for example, move something from the A register to the B register. And we could also supply the data to be moved within a memory variable, so move something from var1 into the A register, for example. Those are all different examples of addressing modes within the CPU, specifically for assembly language. Now, the first part of this lab is actually just going to be review, and we're going to define some things that we've talked about already. Now the second part is going to be a little bit different. We're going to throw in arrays and pointers. And as you're going to discover, arrays and pointers are really not that difficult. They're just going to be an extension upon the addressing modes that we've already learned. So, on that note, let's get started. So, all in all, for x86 assembly, there are actually 6 different forms of addressing. The first of these is register addressing, which, as you can guess, probably has to do with registers, and we'll find out about that shortly. Following that, we have immediate addressing, and I'll go ahead and give you a hint that has to do with constants. Following that, we have direct addressing, and I'll also give you a hint for that one, that has to do with variables, using variables to supply data to instructions. The fourth one is register indirect addressing, and that is actually going to show us how to work with pointers in assembly. The fifth one of our 6 forms of addressing is direct indexed addressing. Now, the indexed keyword here, that should tell you that this one probably has to do with arrays, where you have to index maybe past the first element to get to the second one. And if you were thinking that, you're correct. That is one way to work with arrays. And finally, number 6, base indexed addressing. This is actually going to be another way to work with arrays. However, there's an important distinction between 5 and 6, and it's very important that you don't confuse the two, and you'll see what I'm talking about after we get to those at the very end of Lab 4. But before we talk about any of these 6 forms of addressing, let's first talk about the very important distinction between the terms data, operands, the result, and what I like to call the post-op location. The terms data, operands, result, and post-op location are simply going to assist us in defining what form of addressing we're using in a particular assembly instruction and where that form of addressing is being used for that instruction. And really the best way to illustrate the difference between these 4 terms and how they apply is just to work with an example. So let's consider a very basic move instruction. Let's say that we want to move something from the A register, and let's put it in the B register, just because. Okay, so this should look pretty familiar to you already, the syntax at least. We want to move something, and where do we want to move it from? Well, we want to take it from the A register, and we want to copy it over to the B register. Now, let's start off by talking about data and operands. The data of an instruction, in the case of a move, is what you want to move. So, in the context of our instruction here, what do we want to move? We don't want to move the A register. What do we want to move instead? We want to move what's inside the A register. We want to copy the value within the A register and place it in the B register. The value in the A register is the data for our instruction. So let's make it something so we can better illustrate this example. Let's say right before this first move instruction, let's say we have another move. And for the sake of argument, let's say that we copy the constant 10, denoted by the $sign there, into the A register. So now we're defining our A register to contain the value 10. So now it's clear what the data is, right? In this case, we're copying 10 from the A register into the B register. The data is the value 10 within the A register. Now, what is the operand? Well, the operand of the instruction is any location that contains data. So that means that the A register is our operand for a move. We're moving the data piece 10 from the operand, the A register, into the B register. Does that make sense? So data is simply the constant or the value that you're going to work with within an operand. Now notice that I haven't talked about the B register at all here. In fact, it's not a data, or it's not a piece of data, and it's also not an operand, which kind of give you a hint. It probably has something to do with the result or the post-op location. And if you thought that, well, you're right. The result in this case of a move instruction is going to be what happens at the end. So in a move, it's just really straightforward, and oftentimes it's easy to miss what the end result is of a move, and that's simply that you're taking whatever your data you provide in your source, 10, and 10 is going to be your result as well. You're putting the result, 10, into the B register. The B register, in this case, or the destination, is what I like to call the post-op location. It's the location in which you save the post-operation information. So in this case, we're simply doing a copy, so the result and the data, they're going to be the same thing, but the operand, the location where the data is stored, namely the A register, is distinguished between the post-op location of being the B register in this case. Now, a way to distinguish between all of these is data and operands apply to parameters of an instruction and the data within those parameters before the instruction is executed. So you can think to yourself, what information does this instruction need in order to successfully execute? Well, a move instruction, it needs to know, one, it needs to know where the data is that it's going to move, and two, it needs to know where that data is located. That's defined by the data and the operands, namely the number 10 and the A register. Now, in order to determine the result in the post-op location, you can think to yourself, what is this instruction going to do in the end, and what is it going to modify? Where is it going to save its result? In this case, the result is going to be 10. We're just taking the number 10, not changing it at all, and we're going to save it someplace. The place we're going to save it is the post-op location, or B register. Now, all this seems kind of trivial for the move instruction, so let's do something a little bit more complicated to illustrate the true difference between these four terms. So let's perform an addition. Let's say that we initialize one of our registers here. Let's say that we want to, let's just put the number 1, so constant 1, into, let's use the C register this time. And then let's add ADDL, let's add number 2, and let's add it to the C register. Now, in this case, let's define the data, the operands, the result, and the post-op location. Well, to answer the question about data and operands, let's ask the question, what does the addition need in order to perform its task? Well, by definition, addition takes two numbers and adds them together. So in order to determine what your two numbers are, you need to know where is the data, where are the two numbers that you're adding, And also, you need to know the numbers themselves, right? So, in the case of an addition, what are our two numbers? Well, number 2 as a constant, that's supplied as a constant within the addition instruction. That's one of our numbers, that's one of our pieces of data. Now, unlike the move, addition has another piece of data, because by definition it adds two things together. The other piece of data is within the C register here, which is defined as the number 1. So our two pieces of data in this case are 1 and 2. The operands of this add instruction are the C register and also the constant 2. Now there's an important distinction between the data 2, the numerical value 2, and the constant 2. The operand in this case is the constant 2 as defined here in assembly language, but that has a value of integer 2. So at the conclusion of our addition instruction, we can define then the result in the post-op location. The post-op location is just where the data gets saved, where the result gets saved in the end. See, I'm mixing these up already myself. The result of our addition instruction is what? Well, we want to take the two pieces of data that we supplied via the operands, and we want to produce a result. The result in this case isn't actually shown in either of these two instructions. It's going to be the number 3, right? Because 1 in the C register plus 2 as our source argument is 3. So 3 is going to be our result. And the post-op location is what? Well, if you recall from the way an addition instruction works, where it saves the data is specified also by the second parameter. So that means that our result of 3 is going to be stored in our post-op location of the C register. So does this make a little more sense now with this complicated example? Let's take it one more step and let's take a look at division. So let's consider the example where we want to perform the operation variable 1 divided by variable 2, given by this assembly code right here. So, because we're good assembly programmers, we remember that in order to perform a division, we first need to clear out the D register if we're doing a 32-bit division. So, we move 0 to the D register, this is nothing new, and then we get ready to do our divide. So, we copy variable 1 and we put it in the A register because we know that the A register and the D register are used as the dividend for any division. And then we simply divide by our divisor, and we remember that division only takes one parameter. The one parameter it takes is the divisor. The dividend is automatically assumed to be in the D register and the A register. So let's consider what the data, the operands, the result, and the post-op location would be for this division instruction. Well, let's think what data or what pieces of information does this instruction need in order to perform its task? Well, a division has a dividend and it also has a divisor. Let's start off with the divisor. As we know, the divisor is simply specified as the single parameter to the division instruction. The data within our divisor is whatever number is stored in var2. That is one piece of data for this division instruction. Where's our other data? Well, it's where the dividend is. We have 0 as a piece of data in the D register that's used by the division instruction. We also have var1, which is in the A register. That's another piece of data that is used by this division instruction. So all in all, a division has 3 pieces of data. It has the D register, which should be zeroed out if it's a 32-bit division. It has the dividend, which is in the A register, var1 in this case. And we also have the divisor, which we're directly specifying as the value stored in var2. Those 3 pieces of information are the data of this division instruction. Next we have the operands. And as we know, the operands are simply the locations where all the pieces of data are. So that makes the D register an operand, the A register an operand, and it also makes var2 an operand for this instruction, because the divisor is specified directly with the variable 2. Now let's think ahead to when after this instruction is completed, and let's consider what happens after division. Well, because it's an integer division, we know that we produce 2 distinct results, right? We produce the quotient, which of course is the result from a division, and we also produce a remainder because it's an integer division. We don't produce any decimal number, we just produce two integers, a quotient, and the remainder. And if we recall from how division works, we know that the quotient is always stored in the A register, and we know that the remainder is always stored in the D register. Thus, whatever the quotient is and whatever the remainder is, those two values are the results of this division instruction. So unlike add and move, which we discussed earlier, division produces two results. It produces the quotient and it produces the remainder. So after we've determined what results this instruction produces, let's now consider the post application. Well, because division produces more than one result, it's going to have more than one post application as well. By definition of a division, the way the division works in x86 assembly is it stores the quotient in the A register and the remainder in the D register. Therefore, the post applications are set automatically every time by division. There's no way we can change this. The post applications are the A register and the D register for the quotient and the remainder, respectively. So you might be wondering, why are we taking the time to define four terms for things that we've been doing all along and we really haven't had to worry about what we've been doing? We've just been doing it, like in this, for example, the move's been working just fine, the add's been working just fine, this division's also been working just fine for all the other labs, and now we're all of a sudden giving these four words to help describe what we're doing. Well, this is actually going to help us determine what type of addressing mode and how the addressing mode is being used in a given assembly instruction. We can actually use a combination of different types of addressing modes in every assembly instruction that we use. So using these four terms here, it's going to help us determine not only the type of addressing mode that we're doing, but also in what respect it's being used within an assembly instruction. We can use one addressing mode to retrieve the data from the operands in the instruction, and we can also use a completely different addressing mode to save the result in the post application or post applications. So, a good understanding of these four terms, data, operands, result, and post application, will put us in a good position to understand how and where we use different addressing modes within any assembly instruction. An addressing mode is basically a way that we get the data from the operands and how we store the result in a post application. So knowing where we get data and where we save data in an instruction will help us determine what addressing modes we're using and how we're using them in each assembly instruction. So on that note, let's begin our discussion of addressing modes by talking about direct addressing. Register addressing is very simple, and it's actually something we've been doing all along. It's simply wherever we use a register to reference some data for our instruction. So, in the example of a move, let's say we want to move the number 10 into the A register. We are using register addressing as the destination parameter of our move instruction. How is it being used? Well, it's moving our result into the post application, where the post application is specified through this register, also known as register addressing. Now, the number 10 is also a form of addressing, but we're not going to get to that quite yet. There'll be two types of addressing down the road from here. So, in addition to this move, let's consider another example. Let's say we want to add the A register to the D register. Now, in this example, we have register addressing in more than one way. We're specifying this source parameter as the A register, and we're also specifying the other piece of data that we're going to add using the D register. That's another operand of our add instruction, and so we're using register addressing for both operands, namely the source and the destination parameters. Now, the data is going to be stored within each of these registers, and we really haven't defined what that's going to be, and we really don't care for this example. All we want to say now is that we're using register addressing here, and we're also using it here for both of our operands. Now, we're also using register addressing whenever we save our result. Now, by definition of an addition, the result is always saved in the location specified by the destination parameter, which also happens to be an operand, just by the way an addition works. This parameter here is not only an operand, it's also the post-op location. And this post-op location uses register addressing in order to store its result. Now, this is really trivial, honestly, for register addressing. This is, again, stuff we've been doing all along. We're now just formally defining it. And so you'll see why we're doing this after we get to arrays and pointers, where things start to get a little bit more complicated. So next, after register addressing, let's talk about immediate addressing. Immediate addressing, like register addressing, is pretty straightforward, and again, it's something we've been working with all along. Immediate addressing is simply whenever we specify a constant as a part of our instruction. So let's do the exact same example that we just did for register addressing. Let's say we want to move the constant 10 into the A register. Now in this case, now that we've defined immediate addressing, we can say that this operand, the source parameter of the move instruction, is also the operand. The data within this operand is a constant, and it's the number 10. This is a form of immediate addressing. The reason it's called immediate addressing is because you can think of the constant as being provided immediately to the instruction. And in actuality, it's being encoded as a part of the instruction. So rather than the CPU having to go out and get the data from somewhere, maybe it has to get it from a memory variable, a pointer, which we'll talk about later, or maybe from a register. It doesn't have to do any of those in a constant. The constant is specified directly as a part of the instruction, and therefore it's immediately available, thus immediate addressing. So the constant 10 is an example of immediate addressing for the piece of data within the operand of this move instruction. Now, as a review from register addressing, we can see here that we're using the A register in the destination parameter of our move instruction, and because it's where the result is stored in the A register, it's the post-op location. And the post-op location is an example of register addressing. Now, you're going to see a pattern as we go through all these different forms of addressing. You're going to see that the operands, namely where the data is provided for an instruction, the operands are what determines what types of addressing are being used for data provided to the instruction. And the post-op location or post-op locations are going to determine what types of addressing are used to store the result, or results in the case of division or multiplication. Now, before we leave immediate addressing, let's just be safe and work one more example here. This time let's do a subtraction. Let's say we want to subtract 0, which makes no sense really. Subtract 0 from the B register. Okay? So let's say we want to perform this operation, and really it doesn't make sense to subtract 0 from anything, at least off the top of my head. But let's work with this anyway. So in this case, let's start with the B register, because that's something we've already discussed. We know that we're using register addressing here in our destination parameter because this is a post-op location for this instruction. This post-op location is using a register, therefore it's register addressing based on what we've already discussed. But let's look at this constant 0 here. The constant 0 is an operand for this subtraction instruction. Therefore, it is a form of immediate addressing because it's a constant. This operand has a constant, therefore it's immediate addressing. Now, unlike a move, where we only have one operand, up in this example, that was our sole operand, and it was just immediate addressing here. For the subtraction, we have two operands. So recall a subtraction takes the destination parameter and subtracts the source from it. So we've already said that this operand is an example of immediate addressing. It's just a constant being used in the instruction as an operand. This operand here is also a form of register addressing. Why? Well, because it's an operand, and in any operand in any instruction it has to be some form of addressing, whether it's register or immediate, from what we discussed so far. And we're going to talk about the other four as we go throughout this lab. Now, one of our operands is defined as immediate addressing because we're using a constant here, and this other operand here is a register, therefore it's register addressing. We're also using register addressing here because it's a post-op location. Subtraction automatically stores the result in the destination parameter. So this B register is actually a form of addressing in two different ways for the subtract instruction. It's register addressing for an operand where the value in this B register is used to compute the result, and when the result is stored, it's automatically stored in the B register. So again, the post-op location is also defined by this B register here. So let's move on now that we've worked another example for immediate addressing. Let's move on to direct addressing. Direct addressing, like register addressing and immediate addressing, is pretty straightforward, and it's something we've been doing all along. We're just now giving it a name. Direct addressing is whenever we use a variable within our instruction, and that variable either contains some data supplied as an operand to the instruction, or it's where the result is saved given by the post-op location. Let's start off with a basic example again, and let's just use the move instruction like we did for the other two forms of addressing. Let's say we want to move 10, it's $10, and let's say we want to move it into the variable x. So x is a variable defined somewhere within our program using .com. And just for the sake of review, let's actually define x. Let's say that we could either do this way at the bottom of our programs like we've been doing, or we can do it at the top. Let's just say above move somewhere we said .com. .com is the assembler directive in order to allocate space for a variable. .com takes two parameters. The first one is what we want to call that variable, and so we'd want to call ours x in this case. Second parameter, separated by a comma, is the size that you want x to be, the size that you want your variable to be. In this case, we're defining x to be 4 bytes. Why are we choosing 4? Well, I haven't explicitly told you, but we're working with integers here. And you can also kind of get that from the instruction suffix L we're using here, that this data is going to be interpreted as, the constant 10 is going to be interpreted as a 4-byte long data type, or an integer in the case of a 32-bit machine. Therefore, due to the L here, the x should also be capable of storing something 32 bits in length. So we're defining x to be 4 bytes. So anyway, back to the example for direct addressing. We're moving 10 into the variable x. As a review for immediate addressing, we first take a look at this move instruction and we say, hey, it's a move, so it only has how many operands? Well, it's moving something from one place, and that's the only piece of data it needs to get, just whatever you want to move. We're specifying what we want to move immediately as a part of the instruction there as a constant here, therefore that's an example of immediate addressing. The operand for the move is a constant, therefore immediate addressing. Now a move also has a post-op location. In other words, it has a place where it's saving the result. That's x in this case, which is a variable. Any place that we have either an operand or a post-op location as a variable, that's just simply a form of direct addressing. So in this case, the x here is our example of direct addressing, whereas this 10 in the move, that's immediate, as we discussed previously. So again, this is pretty straightforward, and it's just an extension. We're just defining stuff that we already know how to do. Let's work another more complicated example, and this time we have not done multiplication yet, so let's just do multiplication now. Let's say that we move 10, because I like using 10. Let's move 10 into the A register. And let's say that we want to multiply this number 10 by the variable z. And let's say we've defined z already within our program in a similar way that we use .com up here. So if we want to multiply the variable z by the number 10, well, we've already moved 10 into the A register, so step 1 is complete. We've set up the A register because we know multiplication automatically takes the A register multiplied by the parameter for your multiplication. So that means we can say mul z. And the way this will work, as review, it'll take the A register automatically. It'll multiply by the single parameter here, z. So this is z times the A register. Where's the result stored? Well, as again, a review for multiplication, the result is automatically stored in the A register. The result will overflow into the D register if the A register is not capable of adequately storing the result. So in other words, if you multiply two really big numbers together and it overflows beyond 32 bits, then the remaining bits, the most significant bits, will be stored in the D register. But because let's assume that Z is a very small number so that our result is not going to overflow. Let's say that the A register is adequate. So now given that, let's determine what forms of addressing this instruction is using. And let's start off with the move here, just as review and also to start off with the easy part. We have an operand for our move here. This operand is being given in the form of a constant. So we have an example of immediate addressing here. For our post-op location of this move instruction, we have a register. Therefore, that's an example of register addressing. We're saving the result into the post-op location, which is a register, so register addressing. Now, multiplication here, this is a little bit more complicated, and we have to think about a little bit more than just what is shown on the screen. Multiplication automatically assumes that one of its parameters is going to be in the A register. Therefore, by definition of multiplication will always use register addressing for one of its operands, being in the A register. The other form of addressing that you use for multiplication will depend on what parameter you specify here. In other words, it will depend on how you specify the data for this operand. In this case, we're using a variable. Therefore, this is an example of direct addressing. So far for multiplication, we've said that it's using register addressing for the A register, and it's also using direct addressing by the fact that we're using the variable Z as another operand, or as the single parameter for this multiplication. Now we have to consider where multiplication is saving its result. Well, we've already said that it's going to produce a small result. We're going to multiply a small value in Z by the number 10, so it can be stored in 32 bits. That means that our result is going to be placed only in the A register. It won't overflow to the D register. And our result, it's whatever Z times 10 is. That's our result, and it's going to be placed in the post-op location of the A register. Because the post-op location is automatically the A register, multiplication will always use register addressing as the form of addressing for saving the result into the post-op location. Okay, so I know I'm throwing around a whole bunch of terms here, but what we're actually doing is very straightforward. We're using a constant here, and the constant supplies some data for the move instruction. Therefore, it's a form of immediate addressing. We're using a register here. That's where the result is stored. That's another word for the post-op location, because the A register is going to contain the value 10 when this move instruction is complete. Therefore, because this is a register, it's an example of register addressing. For this multiplication automatically assumes the two operands, the two numbers you want to multiply, are going to be in the A register and whatever parameter you specify out here. Well, if one of our operands is going to be in the A register, then it's going to be supplied, one piece of data in our operand is going to be supplied via a register, namely the A register, so that's an example of register addressing. The other operand, supplied as the single parameter out here, can be whatever form of addressing you want to supply this parameter as. We could put a constant here if we wanted to. We could put a register there if we wanted to. But we're choosing to put a variable Z there, therefore it's an example of direct addressing, because we're supplying the data for this multiplication instruction with a memory variable. And multiplication, as we know, stores its results in the D register and the A register. Now, regardless of the size of the result, because it automatically stores its result in registers, meaning that it puts the result in the post-op location being defined as registers all the time, that multiplication is always going to use register addressing to store its result. So hopefully this makes sense. I know it's a lot of terminology again that's being thrown around, but it'll be useful as we work our way through these more difficult examples after direct addressing. So now that we've talked about how to work with data and results in registers as constants and also using memory variables, let's talk about how to do little things that are a little bit more complicated. Let's work with arrays and pointers next. Now, before we can talk about the other three types of addressing in assembly language, namely register indirect addressing, base indexed addressing, and direct indexed addressing, we all need to be on the same page with regard to arrays and pointers. So let's do a quick review. On the left here, you can see that I've drawn a memory map. A memory map is basically a visual representation of what's going on inside the computer, with regard to memory at least. So the left column here, I have hexadecimal addresses, and to the right here, in purple, are different locations at each of these addresses. Notice I go from address 100 to 104, 108, 10C, and 110. Now there's two things I'd like you to notice about this. The first, and perhaps the most straightforward and easiest, if not obvious, point is that this is hex. So instead of counting from 0 to 9, we're counting from 0 to 15, which is why we have this C here. We go from 0 all the way to F and then roll over to the 16th place, in which we put a 1 there. Now, the other point is, notice that we're skipping by increments of 4 here. So 0 to 4 to 8 to C, and then back to 0 again. The reason I've chosen to number it this way is because our examples that we're going to work with are going to be with integers. And how many bits is an integer in a 32-bit machine? Well, the answer is 32 bits. And how many bytes is 32 bits? The answer to that is 4 bytes. That's why we're going to skip by increments of 4 in our memory map here. So on that note, let's go ahead and get started. Let's say that we have just a simple declaration in C here. I have an integer, and I'm going to call that A. So this is obviously not an array, and it's not a pointer either. And I'm starting with just a plain integer here for a reason. I'd like to explain how a variable name corresponds to a particular address within the computer, or within this memory map in particular. Now, whenever we give a variable a name in pretty much any programming language, we choose a name that makes sense to us as the programmer. So in these simple examples we're doing in this video, I'm going to choose names like A, B, C, my variable, things of that nature, because there really is no bigger picture other than the example here that I'm going to be using these variables for. However, in your own programs, you're most likely to choose names that make sense depending on the type of program you're writing. So for example, let's think back to Lab 3. In Lab 3, we wrote an assembly program to classify a triangle. So we had 3 variables, I, J, and K. Each of those represented one side of a triangle, the length of each side in particular. And then we had another variable called try-type. Try-type was used to store the type of triangle that we determined the triangle to be based on the lengths of the 3 sides. So it made sense within our triangle program to name something try-type, as it kind of alludes to that storing information about the type of triangle it is. Now, depending on the program you write, you can name your variables whatever you want to, and we typically choose whatever makes sense to us. Now let's switch gears a little bit and think in terms of the computer. Does the computer really know what the variable try-type is, or what I, J, and K are? And the answer is no. The computer only thinks, or quote, thinks in terms of binary, in terms of on and off states, ones and zeros. So we need a way to take these human readable variables and represent them in a way that the computer understands. And that's where this memory map comes in. For every variable that we write in our programs, it actually has a corresponding address within the computer whenever our program is running. So for example, if I declare int A here, now a combination of 2 different things is going to happen here. The first thing that's going to happen is at compile time. Whenever GCC goes through and compiles our programs, it's going to take all the global variables, including int A here, and it's going to put them in a global segment of memory that's going to exist whenever our program is run. Now the problem is, GCC doesn't know when we're going to run our program, and as a result, it doesn't know what addresses in memory are going to be available to us. That is determined by the operating system. So what happens is GCC will assign an offset to every memory variable within our program, including this int A, and at runtime we'll be given a starting address for our global block of memory, where our global variables will live. The physical location of each variable will be computed using the starting address of our block of memory plus the offset assigned to each variable. So at runtime, whenever we execute our programs, int A, for example, is going to have a physical location within memory, indicated in the memory map here. So let's just say hypothetically that when we declare A and when we run our program later, A gets placed at address 100 in memory. And so I'll indicate that by writing the letter A next to address 100. Now a common point of confusion is that A is not equal to 100. A is not equal to hex 100. A is hex 100. A is another way to say I want to get to the space located at address 100. Now theoretically, if when we were writing our programs, if we knew exactly what location in main memory we wanted to access, we could hard code a hex address and then refer to that address to access the data at it. But that really doesn't make much sense for two reasons. One is that in reality, your chances are at least you're not going to be granted permission to access that specific address that you hard code in your program. And if you do, you may get a segmentation fault if it's not within the space of your program. So it's difficult to determine whether an address you hard code is actually going to be available at runtime. Second reason is, why do we as programmers really want to deal with obscure looking addresses within our programs? We don't. We want to work in terms of variables and names because that makes sense to us as human programmers. The point is that A and address 100 are two different ways to talk about the same physical location in memory. Whether we say address 100 or A, we're talking about these 4 bytes from address 100 to address or through address 103. A good analogy for this is driving to a friend's house. So let's say that you have your friend Bob and you want to go to Bob's house one weekend. So you hop in the car and you drive to Bob's house. Now try telling the computer to do that. Can you really tell a computer, go to Bob's house? And the answer is no, you can't. The computer needs to know exactly where you're going. So in the case of going to a particular person's house, the computer needs to know the house number, it needs to know the street, it needs to know the city, it needs to know the zip code, the state, and all that kind of information in order to get from one point to the house you're trying to get to. You can say go to Bob's house because you're a human and you are capable of thinking at a level as high as that. Computers can't think that way. And so in a similar way with memory variables and addresses here, we can think in terms of memory variables, but for every memory variable we have in our programs, the computer thinks of it a different way. It just thinks of it as this number here. Let's go back to our example now. Let's say that, so what we've done so far, we've declared A, and A is at address 100. A is address 100. They're both the same place in memory here. Now let's say we want to set A equal to something. Say A is equal to 0. Just a very simple line of C here. Now thinking in terms of C and forgetting about this memory map over on the left, we can just know that we're setting A to the value 0. So when we reference A in the future, it's going to be equal to 0. What's happening in our memory map here is A, or address 100 within memory, indicated over here, that location of our memory map is going to be set to 0, like so. So both A and address 100 have changed values. Whatever was there is now equal to 0. We think that we're setting A equal to 0, but the computer is actually setting address 100 equal to 0. Now for just plain variables like integers here, this seems like a lot more information that I'm telling you just to do something you already know how to do. But this will help you with pointers and arrays, especially whenever we talk about how to do them in assembly. So let's extend this example now by throwing in a pointer. The way we would do that in C is we'd say what type of pointer we want it to point to. That's an integer. Then we put an asterisk. The asterisk is how we declare a pointer of a certain type in C, and let's just say we want to call it B. So at the conclusion of this line, I've declared an integer pointer B, and what that means is that B, whatever address B gets allocated to in our memory map over here, the contents at B is going to be an address of an integer. So let's say that just like we drew A in our memory map over here, let's also put B. And let's say that B is simply located at address 104. Now the question is, what needs to be filled in the blank here? And the answer is an integer address, an address of an integer in memory. And so based on what we've already done, what's a good integer we could use? Well, it's A. So let's direct B to the location of A. The way we do that in C is simply by setting our pointer B equal to the address of A. And in C, the ampersand symbol, indicated right here, that says give me the address of A, or in other words, don't give me the variable A, or don't give me the contents at A, give me what the computer thinks A is. So instead of setting b equal to 0, what's going to happen is a is going to be converted into its address form. The address form of a is 100. So b is going to be set equal to 100. So we're setting address 104, which is b, equal to address 100. So now what we've done is we've initialized our pointer b, and it's pointing to a, which is an integer. So let's do something now. Let's say that we want to change the value of a by using our pointer b. The way we would do that is we would use the asterisk notation again in C, and that's called dereferencing. We would dereference b, and we'd set it equal to something else. So let's say we want to change the current value, and let's rewrite it to 10. So we're going to make this 0 over here 10. The way this works is as follows. B is an address in memory. What is the address of B? The address of B is 104. What's actually happening is we're going to address 104 in memory, and if we were to omit the asterisk in front of B here, we'd just be setting address 104 equal to 10, which would take address 100 here and replace it by 10, and that would break our pointer. What this asterisk says to do is it says take the address in B, so B is address 104, the address in B is address 100. Take that address and go there. That's called dereferencing that address. So go to address 100, so now that takes us up to A here, and set that location equal to 10. So our 0 then becomes a 10. And so that's how we would dereference a pointer in C. Now let's say that we want to extend our example a little bit further here. Let's say that some time goes on and we have another integer, c, and let's say that gets initialized to 20. And so c is a variable, and so it's going to have a corresponding location in main memory. So for the sake of argument, let's say that c gets placed way down here at the bottom at address 110. Because we know some things have happened in between this line and this line, and so these may be occupied with something else in memory. So let's just say c gets put at the bottom here. So when we declare c as an integer and set it equal to 20, we're going to set the address of c equal to 20. The address of c is address 110. We're going to set that equal to the number 20. Now let's say that we want to access c by means of our pointer b. Well, we have a problem as it stands right now. Right now, where is b pointing? B is still pointing us to A. So if we wanted to get the value at our pointer B, or get the value that our pointer B is pointing to, it would take us from address 100 up to here, which is A, and then we'd get the value 10. We first need to redirect our pointer to point to C, and we can do that in a very similar way as when we initialized our pointer to the address of A. So we could say B is equal to the address of C. And what that does is that takes our pointer B and it rewrites it with the address of C in this case. What is the address of C? C is address 110. So that means our pointer B is now going to be address 110. And so we could do something very similar to when we set the value at our pointer B to 10 up here. We can do that also for C if we wanted to. And actually, instead of setting it, let's say we want to access it, just to throw in a different type of example here. Let's say, I know this isn't the exact syntax for printing something. There's many ways to do this in C. But let's just say in general we want to print, let's say we want to print C. What would happen? Well, if we just print our variable C, we're going to print out whatever is at address, the address of C. The address of C is address 110. What's there is 20. So this would print out 20. Let's try and print 20 using our pointer B now, which we've initialized to the address of C. The way we would do that would be print. Now, if we just said print B, what that would actually do is it would do the same thing that we did when we said print C. It prints the contents of the address, or at the address of C. The address of C was 110. The contents there was 20. So extending that concept to the second print of B here, what would happen is we'd go to the address of B, which is 104, and we would print the contents there. The contents is this hex address 110. So we would just print out to the screen address 110. That's not quite what we want to do with the pointer. So to fix this problem, we need to dereference it, and that's using the asterisk notation here. So if we add an asterisk in front of our pointer, what we would actually do is the following. We would go to the address of B. The address of B is 104. We go there, and without the asterisk, we would just print 110. But because we include the asterisk, what that says is go to the address of B, get this address, get the contents of B, and go to that address. So that takes us all the way down to address 110 here. Then print the contents there, which is 20. And so that would print out 20. So what we've done here is just a very basic example of integer pointers in C. This example can also be extended to other data types. There's no reason we had to work with integers here. We could have used characters. So we could have had a character A at the top here. Instead of an integer pointer B, it would be a character pointer B. In other words, B would contain an address of a character. And then we could have done everything in a similar fashion throughout our example here. Now, regardless of what type of data our pointer points to, so if this was a character pointer B, the size of our pointer would still be 4 bytes. So in other words, our pointer B here would still consist of a value from address 104 all the way through address 107 up until the start of address 108. The reason for that is and it's kind of counterintuitive. You think of a character in a 32-bit machine as being 1 byte, so why wouldn't a pointer to a character be 1 byte as well? The answer is that a pointer is an address. And a pointer in a 32-bit machine needs to be able to address any value within our address space. Our entire address space of our computer ranges from address 0 all the way up to address all ones, which is 32 bits, all ones in it. We need to be able to address a character or an integer or any data type within that address space. And so how many bits does it take to address all zeros 32 bits to all ones 32 bits? Well, the answer is, of course, 32 bits. And how many bytes is 32 bits? As we said before, 32 bits is 4 bytes. Therefore, all pointers within the computer are always going to be 4 bytes. And so that's all I have to say about basic pointers. Let's now talk about how to work with arrays and then how to work with pointers to arrays in C. Now, a little bit simpler than pointers is an array. And this will be trivial if you understood the last example with pointers. An array is simply a block of memory, a continuous block of memory within a program where you have more than one data type in a row. And for example, you can have an integer array where integers of a data type and you have multiple integers sequentially, one after another. The way we would do that in C is say like int a, so we wanted to have an integer array of length 5. We denote it with the square bracket notation right here. And that's how we would declare an array. And so just like regular integers, our array A, in this case, would get mapped to some location in memory, wherever that variable happened to be allocated. Let's say that it's allocated at address 100 here, just for simplicity. So at address 100, that's also known as A. We can set elements of our array using this same square bracket notation. So for example, we could say A of element 0, and remember, when it comes to programming, lists or arrays, for example, start at element 0, they don't start at 1. So element 0 of array A, let's set that equal to 10, for example. And so what that would do is, just like our previous example with pointers, is we'll go to variable A. Variable A is defined to be address 100, as we've written here. So we'll go to address 100 and set that equal to 10. The 0 here says that's what's called the offset. How many places away from 100, or how many places away from the start of A do we want to go? So the way you'd compute that is as follows. This is basically the index of your array, And how far you go in your memory map depends on the type of array you have. Now, we're working with an integer array, and we'll assume that we're also working on a 32-bit machine so that each integer is 4 bytes apiece. That happens to be how I've drawn my memory map here too. So each slot of the memory map consists of 4 bytes. So this would be position 0 of A, this would be 1, 2, 3, 4, and so on. Now, if we wanted to set position 0 equal to 10, this says go to the address of A, which is 100, and increment 0 times the size of A bytes. Well, an integer is 4 bytes, but that it really doesn't even matter because we want to increment 0 this time. So we're going to go to address 100 plus 0 times 4, which is still 100, and we're going to set that location equal to 10. That was a lot of explanation for something that was relatively straightforward. But let's try and do something slightly more complicated now. Let's go to the first element of A. Let's set that equal to 20. So the way that would work is we go to the address of A. The address of A is 100. 100 plus 1 times the size of A. Each element in A is an integer. So an integer is 4 bytes. So 100, which is A, plus 1 times 4. We'll set that location to 20. 100 plus 1 times 4 is 100 plus 4, or 104. Set that location to 20. Likewise, we can go even further. A of 2, that is a square bracket. A of 2, just keep our pattern of 10s here. A of 2 is equal to 30. Again, it goes to the address of A. Address of A is still 100, that hasn't changed. And then we want to go to the offset 2. And to convert that to bytes, it's the size of each element times the offset you want to go to. Each element is an integer, so an integer in a 32-bit machine is 4 bytes. So 4 times 2 plus the base or the value of A in our array, which is 100. So 100 plus 4 times 2 is 104, and another 4 is 108. So that location we would set equal to 30. Now you can continue this pattern on up until we get to element 4 of our array. Elements 0, 1, 2, 3, and 4, that makes up an array of size 5, because remember, everything starts at 0. However, rather than working our way up to that and repeating the same thing we've been doing, let's try and do this instead. What happens if we set A directly equal to a number? Let's say we want to set A equal to 40. Well, this is an integer array, and so you might think it's a little bit different than an integer, but in fact it's not. Let's apply the same technique that we did just for regular integer and try and figure out what's going to change in this memory map. What is the address of A? A is 100. So let's set address 100 equal to 40. So we go to address 100 over here. At address 100 we currently have 10. But we're overriding that with 40. So actually, the fact that we included this 0 in brackets here to initialize element 0 of A to 10 originally, we really didn't even have to do that. And if you want to set the 0th element of an array equal to something, or alternatively retrieve something from the 0th element, you can choose to use these brackets, and in my opinion at least, this increases the readability of your code, or you could just simply treat it as an integer. Every time you include something in brackets like this is specifying how many bytes away from the base of your array, from where A is defined to be, you want to go. So if you have a 1 here, that's 1 times the size of an integer. 4, 2 brings you here, then 3, 4, and this would be the end of our array here. So this is element 0, 1, 2, 3, and 4. It's only necessary to include the brackets here if we want to work with something other than position 0 of our array. Now, just like we can have pointers to integers, like we did in our previous example where we had B pointed to the address of A, and we could indirectly access A via B, we can also have pointers to arrays. So let's try and do that now, given what we've currently done in this example. Let's say we have an integer pointer B, and let's set that equal to the address of A. And let's just say that variable b, so our integer pointer b, let's just say that it gets placed down at address 100 here. I mean, it could be anywhere within our program, but let's just say it goes down here just to show that the pointer, I mean, you could have gaps in between your variables. It really doesn't matter. It just depends on how your program is compiled and how the operating system decides to load things up in memory for you. So let's place b down here at address 120. So we have a at 100, that's our array, and we have a integer pointer b that's pointing to the address of a, and our pointer b is going to be located at 120. Now, because we're setting it equal to the address, that's the ampersand, its ampersand specifies the address of what follows it, the address of a. What is the address of a? Well, from what we've already done, we know that the address of a is 100. So that means that b, our integer pointer b, is going to be set equal to address 100. And so just like we did in our previous example, we can dereference our pointer b to access whatever it's pointing to. In this case, it's an array. It really doesn't matter where it's pointing to, but we can access it using an asterisk again. So we could say what b is pointing to, set that equal to 10 for whatever reason. So let's walk through this. We go to b. Where is b in memory? b is at address 120 here. So go to b and get the asterisk says get the address at b and go to that. Dereference that address. So at b is 100. So we'll dereference that by going up to 100 and then set that memory location. Set the location at 100, which is this slot right here in our memory map. Set that equal to what we want it to be, which is 10. So now we're replacing the 40 with a 10 again. So that would be another way. If we had a pointer to an integer array, we could set the first element, or the 0th element of our array, simply by dereferencing the pointer like that. What if we wanted to do something a little more complicated and access an element further on down in our array, but using a pointer instead? The way that we can do that in C is simply by using the bracket notation again, except this time we're going to have a pointer thrown into the mix. Let's say that we want to set the very last index of our array, so that would be element 4, 0 through 4, that makes up 5 elements. Let's say we want to set element 4, so 0, 1, 2, 3, and 4 right here. So we want to go to address 110. Let's say we want to set that equal to 90. Now the way that we're going to go about doing this isn't necessarily going to be intuitive from what we've talked about so far. Now, notice up above where we used the square bracket notation to index into a static array A. And so remember the way we did that, or the way that worked, was A is an address, and we simply added the index times the size of each element to the address of A. So for example, to go to A of 0, it'd be 100, which is the address of A, plus 0 times 4. Or to go to index 2 of A, it'd be 100 plus 2 times 4, or 108, and that's where we set A to 30. The square bracket notation there just simply indexes into an array. However, if you have a pointer to an array, which is what we have now with B, there are two different ways that you can access elements using this pointer to the array. If you want to access the 0th element of the array, you need to dereference the pointer explicitly, saying go to the address stored in B. The address stored in B is 100, so go there and store 10, which is what we did for this most recent example. Now, if you want to go to an offset other than that, you can either use pointer arithmetic, which we won't get into in these basic examples, or you can use the square bracket notation again. If you have a pointer to an array and you use the square bracket notation, it will do the dereferencing for you. Now, it might look like you're accessing just a regular array, but because you're writing this in C, C is detecting when you compile your code that B is an array, and so it's using these square brackets to do the dereferencing for you. So it knows whether or not you're simply accessing an element with an array or an element from a pointer to an array. So let's say that we wanted to do the example we just discussed. Let's say we want to go to the fourth index of A, so A0, 1, 2, 3, 4, and set that equal to 90. The way we would do that using our pointer B is simply like this. B square brackets 4 is equal to 90. And because B is a pointer, the dereferencing of this pointer is going to be done automatically. There's no need to put an asterisk, the dereferencing asterisk, in front of B. And so this can be counterintuitive. However, the way to keep track of what the square brackets are doing depends on, the way to keep track of that is simply to know whether or not you are simply indexing into an array, like we did for A here, or whether or not you are working with a pointer, which is what we're doing for B here. So now let's walk through what this instruction is actually doing. Because B is a pointer, B is going to be dereferenced, and then we are going to increment 4 times the size of each element number of bytes. Each element is an integer. This is an integer pointer. So we're going to increment 16 bytes from where B is pointing. B is pointing to address 100. So this syntax, the square brackets here, because B is a pointer, it's going to automatically dereference the address stored in B, which is 100, which will take us up here, and then we are going to increment by the size of each element times the index we put within the brackets. So we'll go up 16, which is going to take us up to address 110 here. And so that is where we're going to write 90. Again, this can be counterintuitive because the square brackets can mean two different things depending on how you apply them. Just like plus, minus, multiplication, and division are operations within C, brackets are also operations or operators. If you apply brackets to just an integer, like we did up here, because this is an integer, the brackets are going to mean something different. They're going to mean just add this index times the size of an integer to this address and go there, like we did for all the examples in orange here. But if we're applying the bracket operator to an integer pointer, the pointer is first going to be dereferenced using these brackets, and that's just the way it works. So now that you have a basic introduction to arrays and pointers in C, let's carry this concept over to assembly. Let's learn how to use the latter 3 addressing modes in assembly language to work with arrays and pointers. Well, a very observant viewer might note that we just talked about direct addressing right before we started giving a brief introduction to arrays and pointers. And if you recall, direct addressing is how we work with variables in assembly instructions. It's whenever we save the result to a post-op location or we retrieve some data from an operand. Now, you can actually use direct addressing plus a little extra information I haven't told you that yet to work with simple arrays. And so let's talk about that now. Let's say that we have, and so over on the left here, this is a memory map just like we did before. Now, let's say that using assembly, let's work with an array. Let's say we want to call it A. Now, by the way we allocate space for an array is the exact same way that we would do it for regular data types that we've discussed so far, namely integers. So how did we allocate space for an integer? Well, if we don't care about initializing it, we simply use .com, right? Say .com. Now, what's the first argument of .com? The first one is the name you want to give your variable. Let's call ours x because we want to call it x for whatever reason. And we have a comma. And then the second parameter of .com is the size that you want to give your variable. Now, it's the size because, remember, in assembly, we don't really, well, we as programmers care, but assembly language, it does not keep track of what type of data you're working with. So we have to specify the size for the given type of data. So if it's an integer, the size would be 4, because an integer is 4 bytes or 32 bits in a 32-bit machine. Now, you can specify whatever size you want to. So let's say we want to make a 3-element integer array. What is the size of the entire array? Well, a 3-element integer array consists of 3 integers. Each integer is 4 bytes. So the entire size of the array is 3 integers times 4 bytes per integer, or 12 bytes. And we can actually specify that directly in our .com instruction. So in this case, rather than just getting space for an integer, we're getting enough space for all 3 of them, and that space is going to be contiguous in memory. So let's go over to our memory map now. Let's say that our variable x, let's say that it gets placed at address 100 here, so I'll write that over there. So what that means is that at address 100, we have x. That's nothing new. Now, at 100 plus no offset for element 0 of the array, it's going to be stored right here, just like it would be in C. So if we wanted to say x square brackets 1, that would be at 104, just like it would be in C, and x square brackets 2, that would be 2 times the size of the element of the array. It's an integer, so 2 times 4, that brings us from 100 to 104 to 108. 108 to 10b, those 4 bytes are the bytes of our 12 here, allocated for our 3-element integer array. Now, what I've just shown you is how to declare the space for it, and I kind of outlined how you would access that space in C, just talking about it. Now let's see how you would actually do that in assembly language. And it turns out it's going to be just an extension of the concepts that we already know how to do in C. Let's say that we want to set the 0th position of our x array, so this space here at address 100, let's say we want to set that equal to -1. And so the way we would do that in assembly is we would say move L, a constant $(-1), comma, and where do we want to put that -1? Well, we want to put it in the 0th element of our array x, our integer array x. Well, remember, x is just an address of some place in memory that's been provided for the storage of our array. That's at address 100. And so we can simply just work with this like we have any other variable and just put x there. So we're going to move the -1, we're going to copy the constant -1 into location x. Location x is 100. So -1 is going to be placed right there. So nothing different so far. Now, let's try and set the first element, which is at address 104. Let's say that we want to set that equal to 0. So likewise, we can say move L, constant $(0), and now where do we want to put it? Well, it's going to be based on x, I'll give you that much, so we'll put x there. But what's that going to do if we just leave it like that? Well, we're just going to go to the address of x. The address of x, as we see in our map here, is 100. So doing that, we're just going to overwrite the -1 with our value 0. But what we actually intended to do, and I'll try and squeeze that in as a comment here, we intended to set x of 1 equal to 0. And whereas this up here, this is setting x of 0 equal to -1, like that. So as we have our code right now, this is going to overwrite our -1 with a 0. What we want to do instead is go up to this next position. And the way we do that in assembly is actually really straightforward. What we're going to do is manually add an offset to x such that we get to the position, namely address 104, that we want to write our value to. So let me move this a little bit so I can squeeze this in. We want to add to x however many bytes it takes to get to position 1. Now remember, in assembly, we don't know, or assembly does not know what type of data we're working with. We have to take that into account ourselves as assembly programmers. So unlike C, where we can simply just specify in brackets here, I want to go up to space 1, and C takes care of the fact that it's actually 4 bytes you're going up because it's an integer array. In assembly, we have to do that math with bytes ourselves. But it's actually really simple. Just x plus, and then the number of bytes you want to skip. So x plus 4. And there is no space in between x, the plus, and 4 here. That's one parameter for this move instruction. So, and that's it. So we're going to move 0 into the address of x. The address of x is 100. But before we go and move 0 there, we want to add 4 to that address. So 100 becomes 104. So we're going to go to address 104 and we're going to write our value 0 there. It's pretty easy, right? Now, we have a 12-byte integer array defined by x here, so let's do something with the very last element, or the second element of our array. Let's say we want to set it equal to element 0. So we want to take the value in element 0, which is this -1, and we want to set it equal to 108. Now we could just move -1 into x plus 8, but let's say programmatically we want to do this. So sometime from now, we want to access the 0th element of our array, which this is going to work just like you would think. Move L x, so go to address 100, which is x. We need to copy that to some location. Let's say we move it to the A register. So now we have -1 stored in the A register. Now we want to move that into x of 2. So we can then move it from the A register, which is our temporary location. And then let's do the same thing again, except this time we want to access element 2. So element 2 is, remember the math we did for an integer array in C, it was the value in our brackets, which would be a 2 in this case, times the size of each element. So each element is 4 bytes, so 2 times 4 is 8. But we have to do that math ourselves in assembly, so it's x plus 8. So skip from address 100 to 104 to 108. So 100 plus 8 is 108, and write that to be whatever is in the A register. What's in the A register is whatever x was. X was 100, so that -1 got copied into the A register. So we're going to be copying a -1 also to address 108. Now let me ask you this question before we leave this topic. Why did we have to split this instruction, copying -1 from here to here? Why did we have to split this up into 2 different instructions? Well, in short, the answer is that we were limited to one access to main memory whenever we go get data for an instruction. The fact that we had to go to x in memory to get that value, and then we wanted to set that value also equal to something in memory, x plus 8. If we were to put x plus 8 up here, this would be an access to memory, and this would be. And so that's an illegal instruction. Our code would not compile, actually. So using the A register, we copy our value first to a register. So we have one memory access in this instruction. Then we copy it from our register. So we're moving -1 from our A register into x plus 8, which is x position 2 of our 3-element array. And so in both instructions here, we have one access to main memory, which satisfies that requirement. So now that we've talked about how to work with arrays using direct addressing, let's actually talk about how to do pointers now. And so we're going to talk about register indirect addressing next. So up next we have register indirect addressing. Register indirect addressing is what we use in assembly whenever we want to work with pointers, or an extension of that is whenever we want to work with pointers to arrays. So like all my examples here, on the left I've got a memory map, and in our memory map that's where we're going to illustrate what's actually going on with register indirect addressing. So let's say that we want to declare a pointer in assembly language. The way we would do that in C is we would declare the type, which would be the integer if it was going to be an integer pointer, and then we'd use the asterisk to denote that's going to be a pointer, and then we would give it its name, like int pointer or int asterisk a, for example, if we wanted an integer pointer a. The way we do that in assembly is like we would declare any other variable. We can do that using .com. So let's say that we have an integer a, and let's say that's equal to 0, and let's say that we have an integer pointer b. Now let's try and access a by using our integer pointer b, and let's do that in assembly. Well, the first thing we need to do is, like I said, we need to declare a and b. So if a is just going to be an integer, we already know how to do that. We can do that directly using .com, .comm, the name of our variable, a in this case, and the size of our variable, 4. Now, that's good for a. Let's do b now, which is going to be our pointer. .com, pointer b. Now, the question is, what size should our pointer be? Well, all pointers in a 32-bit machine are 32 bits or 4 bytes. They must be able to address every possible address within the computer. Therefore, in a 32-bit machine, they're 4 bytes, or in a 64-bit machine, they'd be 8 bytes. But because we're doing 32-bit assembly, they're going to be 4 bytes. So the size of our pointer is also going to be 4, no matter what type of pointer it is. If it's a pointer to a character, it's also going to be 4. If it's a pointer to a short, it'll be 4. Pointer to a long, it'll be 4. And of course, our example here of a pointer to an integer, that's also 4. Now, let's do something with our integer a and our integer pointer b. First, let's initialize a. So let's say a, let's set it equal to 0. And let's denote what we're doing in our memory map like we have done in our previous examples. Let's say that a is actually located at address 100. So I'll denote that in orange there. And let's say our integer pointer b, let's say it gets placed down here at address 110 for some reason. And so currently we have a equal to 0. That's what our memory map would look like at present. Now, because b is an integer pointer, we need to initialize it. So, and if we want it to point to a, it needs to be initialized to the address of our variable a. The address of a is 100. So we need to have a way in assembly language to use that ampersand syntax that we did in C. And the way we're going to do that is actually in a fashion very similar to how we've been working with constants in assembly. So, to illustrate this, let's just begin by doing it. So, we want to initialize our pointer b to the address of a. In other words, we want our variable b to contain a value equal to address 100. So we want to move the address of a, which is actually done using the $sign in assembly. We want to move that address to our variable b. And so this is actually the exact same syntax, like I said, that we use when we work with constants. What this $sign does is in essence, it's the exact same thing as the ampersand that we would use in C. The $sign says, give me the numerical representation of what follows it. What's following the $sign here is our variable a. We know a as a, but the computer knows a as address 100. So we're saying convert a to its address. So in other words, this is going to become 100. Move 100 into whatever the destination is, which is b in this case. So our memory map is now going to contain address 100 at location b. Now, let's take a step back and think about the $sign. It's saying, give me the numerical representation of whatever follows it. We can actually think of constants in the exact same way. So in the case of this 0 here, we're saying, give me the numerical representation of what follows this $sign. Well, what's following the $sign is a 0. So we're just going to convert this 0 to itself, which is 0, all zeros in binary, and move that into our variable a, which is what we've done in our memory map here. Now, using the $sign in this fashion to get the numerical representation or the address of a variable is how we would do this for global variables. We have yet to talk about local variables, and as we're going to learn in Lab 5, local variables live not in the global variable space in memory, but they live on the stack instead. And so we're going to have a completely different way of getting the address of a local variable than using the $sign. But this is how we're going to do it for global variables for the time being. So again, $sign says give me the numerical representation or give me the address of a and move that into b. That's equivalent to the ampersand syntax in C. So this is just like b is equal to the address of a, if we wanted to write that in C. Okay, so now let's access a by using our pointer b. The way that we do that in C is by using our asterisk, also known as dereferencing our pointer. So we would say asterisk b is equal to 10, which would change our memory location 100 here to 10. Asterisk b is 110, what's there is 100, the asterisk says dereference 100 or go to 100 and set that equal to 10. So let's try and do that in assembly. In assembly, we aren't actually going to use the asterisk, but we're going to use a syntax that denotes the same dereferencing. And it's actually just going to be parentheses. So the first thing that we want to do is move the address that we want to dereference into a register. The address that we want to dereference is contained in the variable b. The value in our variable b is at 110. The value in that address location is 100. So when we say move b to the A register, we're copying the value at b, which is 100, and now 100 is going to be in the A register. Now we're ready to dereference. So if we wanted to change A to 10 by using our pointer b, we could say move constant 10 into the address contained in the A register. And we do that using parentheses. So in C, this is the same thing as using the asterisk syntax. So that would be asterisk b here is equal to 10. This is how we would equivalently do this in C. So the asterisk does the dereferencing in C, but in assembly, we can't use the asterisk syntax, though it's actually just done by using parentheses. We first need to move the address that we want to dereference into a register, and then dereference that address here. So address 100 is in the A register. Go there is what the parentheses say, and then once we're there, move 10 into that location, which changes our memory map like so. Now, why do we need to first move the address we want to dereference into a register? Well, the answer is that we are limited, again, by one reference to main memory per assembly instruction. Now, when we dereference this address, are we going to main memory? Well, the answer is yes, because we're dereferencing 100. 100 is in main memory, as shown in our memory map here. In order to get 100 out of B, did we have to go to main memory? And the answer to that question is also yes. Variable B is in memory. We went to address 110 to retrieve address 100, which is what we stored in the A register. Then, once we went to main memory once there, in this move instruction, we could then do our second access to main memory by dereferencing the pointer in this instruction. We cannot combine both of these assembly instructions into one by simply putting our variable B within parentheses there. Now, it's also possible to use register indirect addressing to work with pointers to arrays. So let's say that we have the exact same setup that we have now, where we have B as a pointer to A up top here. So in other words, B contains the starting address of A, which is 100. But let's change it up and say that instead of A being an integer, meaning A is 4 bytes in length, let's change A so that it is 12 bytes in length. So how does that change things in our map? Well, it actually doesn't. Remember, I purposely put B down here at the bottom. And the reason I did that, little did you know, is that I actually wanted to reuse this memory map to show you how to work with pointers to arrays. So now, instead of A just being in these 4 bytes here, it's A of 0 here, A of 1 here, and A of 2 here. So address 100 to 1 through 10B, all the way up until here, is going to be our 12 bytes for A. Now, we would like to be able to access A using our pointer B. Now, we could directly access A using direct indexed addressing with that plus offset that we just discussed. However, this example is all about register indirect addressing, which is how to access an array using a pointer now. So, let's do that. And it's actually going to be in a way very similar to what we just did here. And keep in mind that with direct addressing, we just added an offset. The same principle is going to apply in this example. Let's say that we want to access element 2 of our array, which is address 108 here. Element 0, element 1, element 2. This means that we want to add 8 bytes in order to get to that element of our array. Each element of our array is 4 bytes apiece because it's an integer array. The second element is 8 bytes away, which means that we can perform the computation 2 times 4 is 8, add that to our initial element, or the base of our array, which brings us to element 108. And this is very similar, like I said, to what we would do for direct addressing if we just wanted to say access that position from array A directly, where that would be A plus 8 in that case. However, a pointer to array, it works a little bit different because we need to dereference that pointer. The way we're going to do that is using these parentheses, but we're still going to add the offset, like we did for direct addressing. Syntax will be slightly different though, as you'll see here. So, let's say we want to access element 2, and let's set it equal to 20. The way we would do that is move 20, and you remember, we already have our base in our A register, so there's no need to move that again. That's already been done for us right here. So we want to move 20, and it's going to go into our base, %EAX here. However, if we just left this instruction as it is now, we would be writing 20 to the address within the A register dereferenced, which says address 100, change the content here to 20. That's not what we want to do. What we want to do is access element 2, which is element 0, element 1, element 2. We want to access address 108. Now, to do that, we're just going to add the offset to the left of our parentheses here by putting an 8. And so like direct addressing, where we added the offset using the plus and then the number of bytes we wanted to offset from our base A, 100, so that would take us to 108. If we wanted to use a pointer to our array, namely B, we could move the starting address of our array, which is defined within our pointer, into a register, and then add an offset to that address before we dereference it. So this is address 100 in the A register, plus 8, that's 108, then dereference that, which means go to address 108, which is here, and then write 20 in there. Now this method can also work to access elements within the array. So rather than moving something into an array, like we have in these examples, we can also retrieve an element from a pointer to an array. Now it's worth noting for these examples that this will not work if we wanted to access a variable index into our array. So in the case here where we want to access A2, equivalent C would be A square bracket 2, like that, where we've hard-coded this 2, the index that we want to access into our array, within our C instruction here. So in a similar manner, instead of saying 2 outside the A register, we need to include the size of each element in the offset. So this is 2 times 4, or 8 bytes from the start of our array. We're hard-coding the access to element 2 in assembly here. This would not work. We could not use register indirect addressing if we wanted to access a variable index, like AI, for example. That is the case where we would want to use base indexed addressing, which is actually what we're going to talk about next. The next form of addressing we're going to discuss is base indexed addressing. Base indexed addressing is very similar to register indirect addressing. They both can be used for pointers to arrays or simply pointers to some primitive data type. However, base indexed addressing is a form of addressing that you can use whenever the index that you want to access within an array isn't necessarily known at compile time. So let's say, for example, that we have our array A that we have been using in all of our examples, and let's say we want to access position I of our array. And to do it in C, we would do so using the following syntax. We have the array A, square brackets, or what we use to get to any index within our array. And this time, rather than a constant being in there, we have an I. Now, as we learned from register indirect addressing, we could simply specify a constant to the left of the dereferencing parentheses in order to go an additional X number of bytes, depending on what our constant was. So for example, let's say that I was 2 in this case, and this is an integer array. And let's assume that the starting address, or the base of our array A, is in the A register. So what we would have done is, let's say we want to move 0 into position 2 of A. In assembly, we would have said MOVL $0, that's our constant 0, And then for position 2, it would be 2 times the number of bytes of each element of the array. It's an integer array, so each element is 4 bytes, so 2 times 4 is 8. Put in 8, then the parentheses, and if the starting address of our array is in the A register, we would have just put the base of our array as shown. And so the calculation would have been performed like this. This address in here, which let's say A is actually located at address 100 in our memory map, so this would be 100 in the A register, 100 plus 8, then we dereference, go to that address. So we go to address 108, and then we would write our 0 there. That's what we would have done for register indirect addressing. However, what would we do in the case that we don't know our offset I, or the index I? In other words, we don't know what this number to the left of the parentheses would be. Well, your intuition might say that you could do this. Move 0 or whatever you want into I of %EAX. However, this won't actually work. The reason is that whenever we're saving the result of our move, in other words, whenever we're writing 0 into some location, we're exceeding the number of accesses to main memory that we can perform. We're limited to 1. So we have 1 access to main memory by figuring out what our constant I is. It's also going to be somewhere in our memory map. So we're going to have to go to I, read the value there, and then apply it to this. Well, what's this? This is an address that we want to dereference. And by definition of dereference, we're going to go to main memory. So by accessing our variable I and by dereferencing our pointer, that's 2 accesses to main memory, and we're only allowed to do 1. So this will not work, and that's why we have base indexed addressing. Base indexed addressing allows us to work with variable indices and still access elements within the arrays without necessarily having to know what that index is going to be at compile time. So let's do a base index addressing example. Base index addressing takes on the following general form. So regardless of whether or not you're retrieving something from an pointer to an array in memory, or maybe you're moving something into an index of a pointer to an array, which is the examples I've been doing here, regardless of what type of operation you're actually doing, you can apply this general syntax anywhere within the assembly instruction, but you're still limited to that 1 access to main memory. So in general, base indexed addressing looks like this. You have a set of parentheses, and within these parentheses you're going to have 3 parameters. These 3 parameters supply the information necessary to compute whatever offset you want to go to in bytes. So for A of 2, it'd be 8 bytes total. It's the size of each element of the array, which is, it's an integer array, so size 4 bytes, times the index you want to go to, which if it's 2, that would result in 8. You'd add that to the starting address. So the 3 pieces of information we need to dynamically or at runtime compute an offset into an array is the starting address of the array, or the base of the array. Thus, that's why this is called base indexed addressing. We need to know the index of the array, in other words, what I do we want to go to, and we also need to know the size of each element within the array. That'll tell us how many bytes from the base of the array to go further on in memory in order to get to the appropriate location. So the following 3 parameters are base, that's the first one. The second one is going to be our index. And then finally, the last one is going to be the size. Now, they don't actually look like this with the angle brackets around them. I'm just denoting this for a very general case. So we're actually going to replace base with whatever the base address might be, index with whatever value of I we want to index to, and size with the size of each element of the array. So let's put this to use now, and let's do a simple example. Let's say we want to move -1 into position 3 of our array, and let's assume that array A starts at address 100 here. Now, in order to use base indexed addressing, we really need to have a pointer to our array A. So let's define another variable. Let's call it B, like we've been using for all of our pointers. Let's say that it's allocated down at address 118, and B has been initialized to the starting address of our array. So let's assume that we've done that already simply to conserve space on the screen here, and also because we've already discussed how to do that in register indirect addressing. So let's assume we've already initialized our pointer to the starting address of our array, which means that B at address 118 should contain address 100, which is what A is. So let's say that it has already been initialized for us like that. Now, using that pointer B, let's use that as our base using base index addressing. Let's go to index I, like so, and then we'll apply our size as well. And let's say we want to move -1 into position 3. I think that's what I said. So 0, 1, 2, 3. We're going to go to address 10C. But we want to compute that at runtime. We don't want to hard code anything like we've done in the past with register indirect addressing. So the way we would do that is we first need to specify our base. So right now our base is stored in our pointer B. B is in main memory. So we're going to have to perform one access to main memory to determine what our base is. However, the fact that we're using parentheses here means that we're dereferencing. Because we're dereferencing, that's also another access to main memory. So that means that we first need to move our base into a register in a completely separate assembly instruction. We cannot simply specify B as our base here. So let's use a simple move, say move L B, and let's put it into the B register. The reason I choose the B register is because B is the first letter of base, and so it's common to use the B register as the base in base index addressing. However, there is nothing magic about the B register. You can simply choose whatever you want, whatever register you have available. So, at the conclusion of this line, the value in the B register is the value that is at location B in our memory map. B is 118. The value at 118 is 100. So that is what's going to be in the B register. So that is the base of our array. And as we can see, that's correct. That's the start of A. Now, we need to deal with our index. Our index, let's assume our index is some variable I, and let's say that it also needs to be someplace in memory. So let's say our I gets allocated at address 114. And so we're going to say we want to go to I of 3, but we don't necessarily know this. Let's say I is 3, which would mean that the value stored at I would be a 3 there. Now, is I in main memory? The answer is yes, it's in our memory map over here. And so just for the same reason that we had to move base into a register, we also need to move the value of I into a register because we're still limited to that one access to main memory. So we have two new registers available to us in order to use as indices in base indexed addressing. These registers are called indexing registers, and I'm going to write them on the top right of the screen here. They are EDI, which stands for destination index, and %ESI, which stands for source index. These are two general purpose registers. They're most commonly used for indexing. However, you are more than welcome to use them for whatever purpose you'd like. So now that I've introduced both of these registers, we now know a total of 6 general purpose registers: A, B, C, and D, and EDI and ESI. And so let's use one of those as our index. You can choose whichever one you want, and even if, let's say hypothetically that you have both of those occupied with something in your program, you don't want to use them, you can also use A through D if you have one of those available. But in any case, let's move I and let's choose EDI. So the value in EDI at the conclusion of this instruction is the number 3. So this move I to EDI says get the value at the address of I. The address of I is 114, get the value, which is 3, move 3 into the EDI register. So now EBX has 100, EDI has 3. Okay, so we've taken care of our base, and we've taken care of our index. The last thing to talk about is the size. Well, I have a question for you, does the size of each element of the array change at runtime? And the answer to that question is no. So when you declare an array, you declare it as an array of whatever type you'd like. So in all of our examples, we've been using integer arrays, mostly because that's what your assignments are going to be using, integers and character arrays. The only difference between the two is the size of each element. But if you're going to have an array of anything, that means that you have the same type of data repeated over and over again, whether it's an array of integers, characters, shorts, longs, structures, you name it. But regardless, it's going to be the same size element over and over. So the size isn't going to change, and we can actually specify that as a constant. However, as you're going to see, we're going to omit the $ from this constant, and that's simply due to the syntax required by base indexed addressing. So knowing that, let's continue our example. We've already set ourselves up with the base in EBX, that's 100, the starting address of our array. We've set ourselves up with the current value of our indexing variable I by moving it into an indexing register, and now we know how to specify the size. So let's continue the example by moving -1, I think is what we said, $-1, and where do we want to put that? Well, we want to put that in our base, which is stored in the EBX register, as follows. Now, if we were to simply close this parentheses of EBX, following EBX, that would look an awful lot like register indirect addressing, and it would be. So, from what just as a quick review from what we discussed in register indirect addressing, what would happen is we would take the address in EBX, in the parentheses that would be around EBX would say go to that address. In this case, we're moving, so we're going to put -1 in that address. Our address is in the B register, which is the value of B, which is 100, so we're going to go to 100 and put -1 there. But we know that we want to go to index I. If I is 3, we want to go to not position 0, but 1, 2, 3. We want to go to address 10C. So that's where these other two parameters, the index and the size, come into play. Those are going to compute the correct offset for us. So let's continue our example then. The next parameter is the index, which we know is in the EDI register, EDI, and then finally we have the size, and we just simply put a 4 here. This is very similar to specifying a constant offset like we did for register indirect addressing. There's no $ that we use for this, and that's just due to the way the syntax of these instructions work. Okay, so let's run through this computation. We're going to move -1 into whatever this computes to be over here. So we have our base, which as we know is the contents of B. The contents of B is address 100. So 100, but don't go there yet. We need to compute our offset. 100 plus I, which is an EDI, I is 3. 100 plus 3 multiplied by the size of each element. So 100 plus 3 times 4, which is 12. What is 12 in hex? 12 is C. So 100 plus C takes us to 10C here. We're going to go to that address, which means it's going to take us to here in memory, and we're going to write -1, just as follows. And so that is how you would do a basic example of base indexed addressing. Now, alternatively, let's say that we knew what I was at compile time. If we knew what I was, meaning we knew that I was equal to 3 in this case, that would mean that if we wanted to write this in C, we would have said, this is a pointer to an array, this would be B of 3, like that. And remember the square brackets, if B is a pointer to an array, they will automatically do the dereferencing for us. We do not need to have an asterisk up front, and in fact, if we do put an asterisk up front, your code won't work. But anyway, if we have a constant, that means that we do not need to use base indexed addressing. We could simply use what we know already from register indirect addressing and apply a constant offset to the left of the dereferencing parentheses. So if we wanted to move a -1 into position 3 of our pointer to our array B, and we knew that we wanted to do position 3 at compile time, we could simply use register indirect addressing. And so let's do that now. We would do a move -1, and then the base of our array is specified in the EBX register. If this wasn't there already, we would need to first move the base into A register. We know it's in the B register already, so we'll use that. The B register contains address 100. And the parentheses though will dereference 100, and we're going to put -1 there. But obviously 100 is not where we want to put -1. We want to put it at position 3. This is position 0, 1, 2, and 3. So we want to go to 10C. How many bytes away is that? Well, it's 12. So and that's computed using the index you want to go to times the size of each element. 3 times 4 is 12. And so if we know that at compile time, which we would if we hard-coded the 3 into the square brackets, we could simply use register indirect addressing and put the 12 to the left of the dereferencing parentheses. So let's run through this one more time. We take the base address, which is whatever's in the EBX register, and we know that we move the contents of our variable b into the EBX register up here. The contents of b is 118, the contents is address 100, so we're going to go to address 100 plus 12. 100 plus 12 is, in other words, 100 plus c, or 10c, and put a -1 there. So the only time you really need to use base indexed addressing over register indirect addressing is whenever you do not know at compile time what index you want to go to. So the last form of addressing I'd like to discuss is direct indexed addressing. Direct indexed addressing is very similar to direct addressing, and it's also similar to base indexed addressing. Direct indexed addressing is like direct addressing in that we're going to use a variable, and it's like base indexed addressing in that we are going to be able to use an index that isn't known at compile time in order to access an array. What makes it different from base indexed addressing is that with direct indexed addressing, we are going to directly access an array using the variable name of the array. We are not going to work with pointers to arrays anymore. Pointers to arrays is for base indexed addressing, while direct indexed addressing is for directly accessing an array using the variable name of the array itself, like A in the case of this example. So the best way to introduce direct indexed addressing is going to be by working an example. And so that's what I have over here in purple. We have an integer array A of length 4. We have an integer I, 3, and that's what we're going to use to index into our array. The first thing we do to A is we access a constant offset of 0, so index 0 of A and set that equal to 0. Then we access A of I is equal to 1, and so we're going to know that I is 3 in this case because of our example, but let's just pretend that I could be anything at this point. A of I is equal to 1, and then we want to do the predecrement on I, which says I minus 1, and then apply that new value to A. So A of I minus 1 is equal to 2, and that'll conclude our example. So let's just start from the top. The first thing that we need to do is we need to allocate space for our array. Recall that the way we do that for an array in assembly is simply the same way we do it for any other variable. We can use .com. So .com, the name of the variable, which is A, and then the size. So for an integer, we'd put a 4 here, right? Because we know an integer in a 32-bit machine is 4 bytes. But because this is an integer array, the total size is going to be the size of an integer times the size of the array. So the size of an integer is 4. The size of our array is also 4. Therefore, we're going to put 4 times 4, or 16, as the size of A. The next thing we need to do is declare and initialize our variable I. Now recall there are two ways to do this. We can either say .com I4, where 4 is the size of the integer I, and then we can say move L3 into I, which is a good way to initialize it. However, the move, it has to be executed every time at runtime, which could be rather inefficient. And so the other way we could do it is by using a label I, the .int assembler directive, and then the value we want to initialize that space to. And so just to practice doing that, let's do that this time. So we have our variable I, which is going to define by this label I. We want to get 4 bytes of space, so we can say .int. That'll convert to 4 in a 32-bit machine. And then following .int, we specify what value we want to initialize that space to. And so in this case, we'll give it the number 3. Okay? So now at this point, we've declared and initialized A and I. Well, we've declared A and we've declared and initialized variable I. Now we're ready to access the elements of A. The first access that we want to do is known at compile time. We want to access A of 0. So, what method of addressing do we know that we can use to access a known offset of an array at compile time? And the answer to that is direct addressing. Direct addressing is how we access either a variable or an array. Not a pointer to an array, but that's how we would access an array with a known offset. So for example, to access position 0 of array A and set it equal to 0, we could do that with the following. Move L, constant 0, $0, into array A. Now let's say, for the sake of argument, that A is defined at address 100 here, and let's put I down at address 118, and so now I is initialized to 3. By accessing A directly here, what we're saying is move 0 into the address of A. In our memory map, the address of A is 100. So we're simply going to move 0 there, and that's the same thing as setting position 0 of array A to 0. We could optionally, if we really had wanted to be precise about what we're doing, we could have put a plus 0 here, which would have said the address of A, which is 100, plus 0 bytes. In other words, just the address of A, which is exactly what we've done here. So we've done the first line here. Now we move on to where we would need to use direct indexed addressing. Direct indexed addressing is how you directly access an array using the variable name of the array, A in this case, but you use an index as an offset, which is not known at compile time. So we're using I in this case instead of a constant. The way we're going to do this is actually going to be very similar to base indexed addressing. We need to provide 3 pieces of information in order for this offset to be computed. We need to provide the base of our array. In other words, where does our array start in memory? It starts at address 100 here, so we need to provide that piece of information. We also need to provide the index we want to go into our array at. So index 0, 1, 2, 3, where do we want to go within our array? And finally, the last piece of information we need to provide is the size of each of these elements of our array. How large is each element? In the case of integers, they're all 4 bytes. And so think back to our base indexed addressing. Those are the exact same 3 pieces of information we provided there. We're just going to do it in a slightly different manner for direct indexed addressing. Now, in general, the way we do direct indexed addressing is as follows. We provide a variable, so just the name of our variable, A in this case, followed by open parentheses and a comma. I'll explain why it looks like that in a second. After that, we provide the index, that would be I, and after that, we provide the size of each element, followed by a closed parenthesis. And a variable has an L in it. So, this looks very similar to base indexed addressing. We provide all of the same 3 pieces of information. This is our base defined through our variable. Remember, a variable is just a way we as programmers reference or think about a particular location in memory. Every variable has a corresponding address. So when we say A, what's actually going to be used is the address of A, which is 100 here, and that's effectively the base of our array. So we're providing that piece of information through our variable. Notice that that's the exact same thing as the base that we would have provided as the first argument within our parentheses here had we used base indexed addressing. We're simply moving it to the left of our parentheses. And that's also why we still need to keep a comma here to specify that there is no base. It's being provided out here. Okay? Now, we're also providing the index here. And this is the same thing that we did for base index addressing. We simply just need to use one of our indexing registers, EDI or ESI, or we could use any general purpose register in reality, just to specify what offset we want to go into our array at, or what position in our array. And then finally, we need to provide the size. And so for an integer array, this is just going to be 4. Okay, so now knowing that information, let's complete our example and access A of I and then A of minus I. Now to start with, do you think that we can just specify I within direct index addressing here? Can we put the variable I in here as our index? Well, and the answer to that is, in short, no. And for the same reasons as base indexed addressing. direct index addressing, the fact that we're supplying a variable here means that we're going to main memory in order to access that variable. That's the same way that we did it for direct addressing. Direct indexed addressing is we're still going to memory, starting at the location of our variable, or starting at A in this case, but we're going to add this many bytes to that starting location. So that already meets our maximum of 1 access to main memory. If we put a variable I in here, that would make 2 accesses to main memory, and that's illegal, and our code would not compile. So, like I said, we need to move I into a register, and let's choose one of our indexing registers. I'll choose EDI. Or I think I used EDI for the last example, so I'll use ESI just to show that you can use both. So we move I into %ESI. Okay, so now I, the value at address of I, which is I is 118, the value at that address is 3, so now ESI is going to contain the number 3. And now at this point, we're ready to proceed with direct indexed addressing. There's no need to move a base into a register. We're supplying the value of our base simply by using the name of our variable here. So, in this case, the base, what we want to access is array A at position I. So the base is A. We want to move L, the number 1, into the base of A, parentheses, comma, the index, which we have as ESI now, comma, the size. And so let's walk through what this computation is doing. Oops, and there should be a 1 there, $1. We're moving the constant 1. So let's walk through this computation. We're going to move 1 into this starting address. The address of A is 100, so we're going to move 1 into 100 plus ESI, which we know from our example here, I is going to be 3. So this is going to be 3 times 4. 100 plus 3 times 4 is 112, but in hex, that's 10C, which is right here. And so at the conclusion of this instruction, we're going to have a 1 right there. Okay, so that's pretty straightforward. Now let's move on to the second example we have for direct addressing. We first need to subtract 1 from I first, and to do that, recall that we can use the decrement or decal instruction. DECLI. And I'll put as a comment here, what that's actually doing is I is equal to I minus 1, or alternatively in assembly we could have said subtract constant 1 from the variable I. Now one thing I will point out is that we're doing this to the variable I, which means in our memory map, I is going to change to a 2. Now you might be wondering, why didn't we just decrement ESI directly? Because right now what we're going to have to do is move I back into ESI or EDI alternatively once again. Because remember, we must use a register as our index. We can't specify I directly. So to make our code more efficient, we could have just said decrement ESI. We would not have had to do this move here. But had we done that, and let's just say our example was larger than this, and let's say further on down we used variable I again. Had we forgotten, so if we had done decal ESI and we forgot to move ESI back to I again, and thus updating our main memory's value of I, then we could possibly use the incorrect value of I at a later point. So this is the safest way to write our code, albeit it's not the most efficient way. It is the safest way to do it. And so that's how we're going to proceed with this example. So at this point, we now have the updated value of I in our indexing register, and we can simply proceed with direct indexed addressing like we did in the first case. In this case, though, we want to move 2, so move L, $2, into the base, which is A or address 100, plus ESI, whatever that is, and we know from our example it's going to be 2 ESI times 4 bytes. So let's walk through this. A, the address of A is 100. That's our base. We're not going to move 2 into the base, though, which would be up here. We're going to increment the base, which is 100, plus ESI, which we know to be 2, times 4. So 2 times 4 is 8. 100 plus 8 is 108, and this is where we are going to write the number 2. And at that point, that completes this example. As you can see, direct indexed addressing is very similar to base indexed addressing. The key difference between the two, though, is that direct indexed addressing is used for accessing arrays directly in memory. In other words, we are directly accessing array A here. We are not using a pointer to our array. Now, whenever we know the offset of our array at compile time, in the case here of A is 0, we could simply use direct addressing without the indexing part. And that's what we did up here. We moved the constant 0 into simply A, and this plus 0 is really redundant. So if we had A index 1, we could have moved 0 into A plus 4, where we know the size of each element is 4 bytes, so 1 times 4 is 4. The only time we need to use any form of indexed addressing is when we do not know at compile time what that index is going to be. Okay, now that concludes everything I need to say about direct indexed addressing. Let me talk about one last thing about base indexed addressing. What I'd like to talk about now is how we would work with a pointer to an array of structures in assembly language. Now, you should immediately think base indexed addressing because we're talking about a pointer to an array of something. It happens to be an array of structures now instead of an array of integers, which is what we worked with in our previous examples. But before we get into the details of assembly, let's talk about what it means to have an array of structures and a pointer to an array of structures in C. So here's some example C code. I have a structure, my struct, and it consists of 2 integers, x and y. And a structure is basically a user-defined data type. So in this case, I'm defining a custom data type, and I'm going to call that data type my struct. And it's going to consist of 2 sub-elements, 2 integers in this case, int x and int y. You can have whatever sub-element you want in a structure. You can have a structure that consists of other structures. You could have a structure that consists of mixed data types too, like an integer and a character, for example. But in this case, let's say we have a structure with 2 integers in it. And then what I do down here is I declare an array of these my structures. So instead of an array of integers, which is what we've worked with before, I'm having an array of my custom data type, an array of my structures in this case. It's going to be of length 3, and that array's name is A. Next, I'm declaring a pointer to my array of structures. So this is instead of an integer pointer, which is what we worked with before, this is a struct my struct pointer. So a pointer to at least one my struct, my custom data type. And I'm calling that pointer B, and I'm initializing it to the address of A. So let's take a look at our memory map over on the left here. I have A, let's say for all of our examples what we've done, let's say A, our array is at address 100, that's where it gets placed in memory. And let's also say that our pointer B, in this case, gets allocated at address 120. Now, as it stands right now, this code simply declares and initializes an array of structures and a pointer to that array of structures. What we would like to do is do something interesting. For example, access an element within our array of structures, and then, from there, access a sub-element of our structure, for example, x or y. So we can go to, for example, position 2 of our structure array and then access either element x or y. So let's do that, and I'm going to actually put the C code on the right here just to conserve space. So I'm going to continue what I have on the left in a new column on the right. And what I'd like to demonstrate is how we would work with this pointer to our array of structures using a constant or a known offset into our array. And I'd also like to do it using a variable offset, which should mean that we'd use some form of indexed addressing. So I'll have an index variable that I'll declare as int I, and I'll set that equal to 2 just because. And then, given that, we'll use that as our index, and now let's access elements of our array in 2 different ways. So B is the pointer to our array of structures. Let's go to a constant offset of 1. Now, as we have it here, what would happen is we'd go we would dereference our pointer to our structure array. We would count over one structure from the base of our array. But from here we have two choices. We can either grab X or Y. The way we would do that in C is by using a dot. So let's do X in this case. And let's set X equal to 0. So let's just clear out X. Okay, so that's one example that will work. And another one, this time let's use our variable I. So at runtime, I could be anything. It's a variable. So that means we'll need to use base indexed addressing, because this is a pointer to an array of something, and we're accessing a variable offset. So we'll say b of I. We know I is 2, and that's what we'll use for our example to demonstrate it in our memory map, but in reality it could be anything. And let's access element Y this time. Let's initialize that to -1, just because I'm picking these numbers at random, including the index I of 2. Okay, so now given that in C, let's convert all this to assembly. And to do that, let's start at the very beginning. So the first thing that we want to do is allocate space for our array of structures here. We're declaring an array of structures named A, and it's of length 3. Now the way we would do that in assembly is by using .com. So .comm, the name of our variable, which is A, and then the size. Now what would the size be in this case? If this was an integer array of length 3, it would be the size of an integer, which is 4 times the length of our array, 3, so 12. But this is an array of structures. How many bytes is each structure in our array? The answer is 8. Each structure consists of 2 integers. Each integer is 4 bytes, so 4 plus 4 is 8. That's the size of each structure. Now we have 3 structures in our array. So 8, which is the size of each structure, times the length of our array, 3, is 24. So .com A 24. That is how we will get the space we need for our structure. And so let's say that will get allocated at address 100 in our memory map here. So A and address 100 are the same location. Okay, so the next thing we do is we declare and initialize our pointer to our structure array. So let's first declare it. We'll say .com B, that's the name of our pointer. And then the question is, what's the size of our pointer? Well, this is a pointer to an 8-byte structure. However, the size of any data type a pointer points to doesn't matter. It's the architecture of the system. So if we're working in a 32-bit architecture, that means we need to be able to reference from address 0, all zeros, 32 bits of all zeros, to 32 bits of all ones. So we need 32 bits or 4 bytes in order to reference all that entire range of addresses. So a pointer, no matter what it's pointing to, in a 32-bit machine is always going to be 32 bits or 4 bytes. Okay, so now let's initialize our pointer. Recall that the way we initialize a pointer is similar to how we would work with a constant in assembly. So we would say move the address of A. The address of A, we can get that by using the $ followed by the variable A. And what that says is the $ in any case says give me the numerical representation of what follows it. If we simply gave a number there, like 0, 0 is a number already, so it just gives a 0 in binary. Now if we put a variable, what that's going to do is it's equivalently going to do the ampersand operation in C. It's going to convert this character or string variable name into what the computer thinks it is. So it should give us address 100 in this case. So we're going to move the value of A, so move 100 into B. Now again, this looks like we're accessing main memory twice, but we're not. We're simply doing a conversion in our source parameter. Our single access to main memory is by storing the value in memory variable B. Okay, so at this point, we've declared and initialized our variables. Well, actually we haven't. We forgot about I up here, so let's do I. And to save space, I'm going to declare and initialize I in one line. Remember, the way we did that is using a label I dot int. That's the amount of space we want to get. That will convert to 4 bytes in a 32-bit machine, and then followed by the number we want to initialize it to, and the number 2 in this case. Okay, so at this point, we're done with all of our declarations and initializations from the structure A, the pointer to the structure B, the pointer to the structure array B, and then our indexing variable I. Now we can get to the bulk of our code, which is going to be accessing element 1 of our pointer to array of structures B, sub-element x, setting that equal to 0, and then accessing a unknown element determined by I at runtime, B of I, sub-element y. And so let's work through those examples. So starting with the very first line, we're accessing a constant index of B. Because we're accessing a constant, or known at compile time index, we can use register indirect addressing in order to access element 1, because we know 1 at compile time. The reason is, using register indirect addressing, we can specify to the left of the dereferencing parentheses a constant offset. And so we'll compute that offset in this example. The first thing we should do, though, is move our base, which is the pointer, the value within our pointer B, which is address 100, and I'll indicate that in our memory map here. So, and that should have been set in our memory map. I should have done that earlier when I said move the address of A into B. In other words, move 100 into B. And so that's what B looks like. We still don't know what's in A, but we're about to do that in a second here. So the first thing we need to do is we need to move this base, or move the pointer, into some register so that we can dereference it later. So let's move it into the B register. So move B, the value in B, the value in the variable B, into a register. And I'm going to choose the B register, but you can use whichever one you have available to you. So at this point, the B register will contain the address 100. Now, we can dereference that and set the first element of our array of structures, sub-element x, equal to 0. So the way we would do that is by register indirect addressing. So we want to move a 0 into our base, EBX. So let's leave our code at this right now. What this would do, if you recall from register indirect addressing, is this will take the address in the B register, the parentheses will dereference that address, or in other words, go to that address in main memory. So that's an access to main memory. That'll take us up to 100. And if we just left our code as it is, we would set 0 equal to this address, or this memory location at address 100. And that's not quite what we want to do. We want to go to element 1 of our structure array, sub-element x. Now, we need to do the math here for register indirect addressing. What we're going to do is specify an offset to the left. What does that offset need to be? Well, if we want to access element 1, we need to skip over element 0. Each structure, or each element of our structure array, is the size of a structure. The structure in this case is a mystruct, which is 2 integers, or 8 bytes. So we need to skip over 8 bytes, which will take us from address 100 to address 108. Now, once we get to that, we have two options. We can either access element x or element y. The way structures work is how you declare the elements within a structure. That's the order they're going to be in memory. So, if address 108 is where structure 1 starts of our array, address 108 is where x is going to be. And likewise, address 10C, that is where element y is going to be. So if we simply move up 8 bytes to get to element 1 of our structure array, we're already going to be at the position for x. So all we have to do is put an 8 out to the left here. And so this computation is going to be 100 plus 8, go there, that's what the parentheses say, so go to 108 and write the number 0 there. Now, to help you visualize this array of structures in memory, what I'm going to try and do is write the sub-elements for each element of the array in memory and on the memory map here. So we have the start of our structure array is indicated by A at address 100. At 100, we have an element X. At 104, we have Y. At 108, we have another X. This starts element 1 of our structure array. At 10C, we have element Y, which is the second sub-element of our structure. Remember, each structure has two integers, x and y, and because this is a structure of length 3, we have elements 0, 1, and 2. So we have one more structure to write on the map here. X for position 2 starts at 110, and y is at 114. Now, we don't know what's at address 118 here, or 11C, and it really doesn't matter for this example. There could be other variables there, but we're just going to indicate where our structure array is and where our pointer to that structure array is. So, just to recap what I've done now is we have our structure array A that's indicated by the start of our array at 100. This is an array of structures, not an array of integers. So each element is the size of the structure, and each structure contains an integer x and an integer y. So for the 0th structure in our array, it has x and y, each of which are 4 bytes. For the first element of our structure array, x and y again, each 4 bytes. And remember, we set the first element of our structure array, sub-element x equal to 0, which is indicated at that position. And finally, because this is a structure array of length 3, we have a 0, 1, 2 structure, which is indicated starting at address 110 and then ending at address 117 through 117, starting at 114 for y, ending at through address 117. Okay, so now let's continue this example. We've already done setting element x to 0, and that was kind of a review of register indirect addressing. We simply put an offset to the left of our dereferencing parentheses, and that offset will be applied before the dereference happens. Now, what we need to do is use some form of indexed addressing because we're going to go to a variable offset of our structure array. Because this is a pointer to an array, doesn't matter it's a pointer to an array of structures, but because it's a pointer to an array, we must use base indexed addressing. So let's do that. And we already know how to do base indexed addressing. I'm just going to show you how it will apply to structures here. And it's going to be a little bit different because now we want to access element y. Okay, so the first thing we need to do for base indexed addressing is we need to set up the base of our array. We need to set that into a register, and we also need to set up our index. Well, we just moved the base into the B register to set element x of our first structure equal to 0 right here. And has the B register changed since this point? It has not. We just dereferenced it. So we can reuse the B register, which has the starting address of our array. It has 100 in it already for us. Now what we do need to do is we need to move index I into a register. We are not allowed to use a variable within base indexed addressing because it's already accessing main memory in and of itself. So, and I'll indicate this code over on the right here just to save some space, or because I'm running out of space in this column. We already have the starting address of our array, the base, in the B register, so now we just need to move I into a register, and remember we have EDI or ESI at our disposal. I'll choose ESI, the source index register, and you could use whatever, if both of these happen to be used, you could use A, B, C, or D if one of those is available too. Okay, so now we have our base in a register, we have our index in a register. Now we're ready to perform base indexed addressing to do this very last line here. And we want to move the value -1 into position I of our structure array at sub-element y. So move L $-1, and then here comes our base indexed addressing. First parameter, EBX, that's the base of our array. Second parameter is the index, ESI. And then finally, we have our size, and this size is going to specify the length of each element in the array. For an array of integers, this was 4. For an array of characters, it would be 1, because every character is 1 byte in a 32-bit machine. What is the size in this case? In this case, it's an array of structures, which is a custom data type, and in this case, it's defined to be 2 integers, or 8 bytes apiece. So our size is going to be 8. Now, given what we have so far, let's run through this computation and see where it takes us in our memory map. So, we'll start with our base. Our base is in the B register, the B register contains the contents of our memory variable B. Our memory variable B is at address 120. The contents there is address 100. So we're going to start at address 100 up here, but we're not going to directly access 100, we're going to add an offset to it. The offset will be computed at runtime by the ESI register multiplied by our size of 8. The ESI register contains memory variable I, which I should probably indicate over in our memory map here. Let's say it's here, and remember the contents of I is 2. So continuing this example, we'll take what's in the variable I is at address 11C. The value there is 2, so we've moved 2 into the ESI register. Now we're going to do 100 plus 2 times 8, which is 116 in decimal, but because we're working in hexadecimal over here, that's going to take us to 100 plus 16, or 110. And we're going to set that position equal to -1. But where are we in our structure array? We are at element X right now. What we want to set equal to -1 is element I. That is 4 bytes away from element X. Now, the way to fix this problem is as follows. Recall that in register indirect addressing, we're able to add a constant offset to the left of our dereferencing parentheses, and that offset will be added to the address before the dereference takes place. We can actually do the exact same thing for base indexed addressing. We can put a constant offset to the left of these parentheses. So we're going to do that in order to access element Y here. What offset do we need to apply? And the answer is 4. We're at address 110 right now, 100 plus 2 times 8, which is 110. Now, we want to get to 114. That's where variable Y of this structure is located. So we just need to add 4 bytes. And so we can put a constant 4 to the left of our parentheses. Now you might be wondering, why can we do this? Because we're supposed to be accessing a variable index of our array, not a constant. And by putting a 4 over here, we're including a constant in this computation. But that's okay, because we're always going to be accessing Y here, regardless of what I is. And Y is always going to be an additional 4 bytes away from the start of X in our structure. It's going to be 4 bytes away, just by the fact that this is how the structure was declared. So this 4 is perfectly fine, and no matter what I is going to be, this 4 will still get us to Y. So let's just pretend now that I is equal to 1. If I is equal to 1, and we wanted to set element Y equal to -1, where would that take us? So our base would still be 100, ESI would be 1, and then we're going to say 100 plus 1 times 8 is 108, so that would take us here, but we're adding an extra 4 to it. So 108 plus 4 is 10C, and that's going to take us here. And that's exactly what we would want to do if I was 1 in this case. We would want to set this location equal to -1, which is always going to be Y. Y is always going to be 4 bytes away from the start of every structure in our array. So this is how we would work with an array of structures. The only thing that's different from an array of a primitive data type, like integers, is we would need to sometimes include an additional offset to the left of our dereferencing parentheses, and that's to access any element that is not located at the beginning of each structure. So imagine that if this structure was more complicated and we had int x, int y, and int z, what if we wanted to access int z at any element? Well, we would simply need to change this 4 to an 8, because we wanted to skip over x and y, each of which is 4 bytes. That's a total of 8 bytes we want to skip to get to where z would be located. So you can apply this principle to any type of structure array, really. Now, I hope you forgive me for telling you this now, but I just realized I've made a rookie mistake in my C code, and if I was actually giving this lecture in person, hopefully someone in the class would have spoken up and told me what I've done. Remember, if we have a pointer to any type of array in C, do we need to put the asterisk in front of in order to dereference the pointer to our array? The answer is no. And if you actually tried to compile this code as it is now, it wouldn't even work. The dereferencing is done automatically using the square brackets that I have here to dereference position 1 or position I. So C, the compiler, GCC, will detect automatically that B is a pointer, and it will do the dereferencing for us. So in essence, what I would be doing here is if I actually tried to compile this code, I would say, give me the address in B. The address in B is 100. Go to 100, go to position 1, so position 1 is take us to 108, and that's .x leaves us in the same place. Then we would dereference that again. What is that? That's 0, so that would take us up to address 0 in our memory map, which I can tell you right now, address 0 is not in your program's memory space, therefore you're going to get a seg fault. And I don't even think your code would compile like this. So you should not have an asterisk at all in front of to dereference a pointer to an array of anything. The dereferencing is done for you automatically using the square brackets here. So now that I've corrected myself there, let's talk about one last thing with regard to arrays of structures. What if we wanted to directly access our structure array using the variable we declared it with? In other words, what if we just wanted to forget about this pointer to an array of structures, but instead access our structure array directly using variable A? Well, we can definitely do that, and we can do it in one of two different ways. If we know at compile time what the offset is into our structure array, then, in other words, if we wanted to do maybe A of 2 dot x, and set that equal, let's just continue our pattern here and do -2. If we wanted to do that, then at compile time we definitely know what 2 is, and so we would want to use direct addressing, just like we have done for simply arrays of integers, and I'll walk through how to do that. Now, if we do not know at compile time what index we want to go to, it would look something like this: A of I, and I'll do a dot y in this case. Let's set that equal to -3. If we do not know at compile time what index we want to go to, we cannot use direct addressing. We must instead use direct index addressing, as you probably have guessed. So let's start with the first case where we set A of 2 dot x equal to -2, and like I said, that's going to be direct addressing. And remember, for direct addressing, we simply give the name of the variable, and that will be converted automatically to its numerical representation. In other words, the variable A will be converted to address 100, and that is going to be our base for direct addressing. So we want to move $-2, and we want to put it into A. And so let's start with that. Now we want to go to position 2. And so the way we do that with direct addressing is, remember, we simply add an offset using the plus followed by the number of bytes we want to go to the right of our variable. In this case, to the right of A. So how many bytes do we need to increment in order to get to A of position 2? Well, to answer that, we need to know not only what position we want to go to, but also the size of each element at each position. And this is an array of structures, so the size of each element is defined up here within the definition of the structure. This structure consists of 2 integers, therefore the size of each structure is 4 plus 4, the size of each integer, which is 8 bytes total. So the addition that we perform to the right of this variable A should be the address of A plus 8 bytes for each structure times the number of structures we want to skip, which is just the index of 2. So 8 times 2 is 16. Okay. So that's going to look like the following in our memory map. We're going to take the address of A, which is 100, as indicated in our memory map, and add 16 to that. So 100 plus 16 takes us up to address 110. Remember, this is in hex. And so at address 110, we should be at position X of element 2 of our structure array. So let's verify that right now. Well, we're at position X, but what element are we at? There's element 0, X and Y, element 1, X and Y, and look, there's element 2, X and Y, and element X of structure 2 in this array is at address 110, and that's right where we calculated. So let's write -2 there. Now I know I didn't do this in C up here, but let's just hypothesize about how we would change this if we wanted to access A position 2.y instead. Well, 2 is still known at compile time, and the y component is also known at compile time. We know by the definition of our structure that y is right after x, and x is the 0th element within our structure here. In other words, y is the size of x beyond it. That's where y starts within the structure, so y is 4 bytes away from the start of it. So, if we wanted to access element y at position 2, we would simply need to add another 4 bytes to this offset, and that would make it a plus 20. And so to verify that, let's look at our memory map. A is 100, plus 20 is that original plus 16, which takes us to address 110, plus another 4. And look, there's A of y. So then in general, that's how we would work with an array of structures or an array of anything if we have a known offset or a known index. Okay, so let's work the case now where we do not know necessarily what index we want to access. And let's say we want to access position y within our structure. The fact that we do not know at compile time what I is means that this is going to be direct indexed addressing. Direct indexed over base indexed because this is a variable we're accessing directly. This is not a pointer, unlike up here where we had b, which is a pointer to our structure array. So for any type of indexed addressing, we need to have those 3 pieces of information in order to compute what address of our memory map we want to go to. We need to know the base, or where does the array start. In this case, that's going to be specified with A. We also need to know what index we need to go to, and that's going to be defined by I. We want to increment into A, I positions, and then finally we need to know the size of each element in our array. And so for an integer, that would be 4, but this is a structure, so remember this is a user-defined data type, and our size should be 8 in this case. This integer is 4 plus this integer, which is also 4, for a total of 8. So the only thing we need to do for direct indexed addressing is to simply move our index into a register. But we've done that already. Notice that in our C here, nothing's changed from when we first used our index here to here, and our index is already in the ESI register. Now, had we changed ESI from the point where we used it here for the first access of element I to when we're going to use it again here, then we would need to update ESI or EDI or whatever register we plan to use for our index from the current value of I. But only because 1, I has not changed, and 2, ESI has not changed. Only for those 2 reasons can we reuse ESI again right here. It's going to have the value of I that we want. So now having said that, let's go ahead and do our final instruction. We want to move MOVL -3 $-3, and we're going to put it into A of I at position Y within our structure. So the way we would normally do that is as follows. For direct index addressing, we would have A followed by parentheses and a comma because we're using A as our base, so we omit it as the first parameter within parentheses. Then we put our index, which is ESI, %ESI, followed by our final argument, and that is the size of each element, which is again going to be an 8 here, followed by close parentheses. Now, let's go ahead and walk through and figure out what address this is going to take us to and figure out whether it's exactly what we want. Well, the first thing that's going to happen is we're going to use A as our base. A is address 100, so that will be used as our base. And our offset will be computed by taking our base and adding ESI times the size, which is 8. ESI, we know, has 2 in it, because I has not changed and ESI has not changed since we used it last. So this is going to be 2 times 8 and add that to 100. That will take us to address 116 decimal, which is 110 hex. But is that A of I dot Y if I is 2? And that is not Y. We can see right here that's X. Y is 4 bytes away. So in a similar manner, where we had to add 4 as an additional offset for base index addressing, we also need to be able to have a way to add 4 more bytes to get from element X to element Y using direct index addressing. And as you might have guessed, the way that we're going to do that is by adding a plus 4 right after our base of A. And so that looks very similar to just direct addressing. Now, given that additional offset, let's verify that we're going to position Y here. So we start at address of A, which is 100 in our memory map. We're going to add 4 plus ESI times 8. ESI has 2, so we're going to add 4 plus 16. 2 times 8 is 16, so that gives us a total of 20, which we know 16 takes us to 110 here, and then we're just going to add another 4 to that and take us to 114, and that is indeed position Y. And there is where we're going to write a -3. And so like I mentioned for base index addressing, you can imagine that if you had a more complex structure, maybe 3 integers or 4 integers, the way you would get to an integer further on down, maybe if we had X, Y, and then Z here, we would do a +8 here to get beyond the first integer. So to get to X, we could theoretically put a +0 here, and that would take us to position X. To get to anything beyond X, we have to add an offset skipping over the number of bytes of the prior elements of our structure. To get to Y, the prior element is 4 bytes, so we have to skip 4, which is what we're doing here. If we had 2 integers we wanted to skip, we could do +8, and that would take us to our third integer. But our structure is not that complicated in this example, so adding +4 is all we can really do to get to another element within our structure, because Y is the last element. So on that note, that's all I have to say about arrays and structures. You can do more complicated things than this. For example, you can, instead of adding an offset here, you can subtract something. It might be useful to do that, maybe if you wanted to work backwards through an array. That's also true for direct addressing here, and also for base addressing. You could, base index addressing, you could have a negative offset to the front there if you wanted to. You can even have negative indices, so if you wanted to start at the end of an array and have a negative index where you decrement it every time, you could even make your index negative. The point is, for any form of addressing, all you're doing is performing some math. You take an initial address, which is your base, and then you add or subtract something to or from that in order to take you to the correct location within memory, or to take you to the correct location within our memory map, and for all of our examples. Now, I'd like to take a step backwards and work something a little simpler. What we've talked about so far is how to address things within existing arrays and structures and pointers, things of that nature. And notice how we've declared all of our arrays and structures. We've used .com here. However, notice here, we've declared and initialized our counter I here using a technique we learned in Lab 2. We can declare a label, and that would be the name of our variable, and then we can allocate some space and initialize it thereafter. We can actually do something very similar for arrays, and that's what I'd like to talk about next, how to declare and initialize arrays. One of the last things I'd like to discuss is how we would declare and initialize an array at compile time. Now, why would we want to do this at compile time over runtime? We already know how to declare an array. We can do that using .com, give the name of the array, and then give the size in bytes that our array would occupy in memory, and that would give us the space we need in our executable. And then at that point, we could use one of the forms of addressing we learned about. We could use direct indexed, we could use base indexed, direct addressing, or even register indirect addressing in order to set or retrieve values within our array. We could set values in the array to initialize it. So why would we want to do it at compile time? And the answer is, as you might have guessed, is that it's a little more efficient to do it this way at compile time than it is at runtime. Consider a program that you write once, you get it, you maybe do a little bit of debugging, but then you finally get into a good polished form and you create an executable for it. And then you hand that out to a lot of people to use for themselves. Let's say they run it 1,000 times a day. If you declare a bunch of arrays and you initialize them all at runtime within your program, those arrays must be initialized every single time the program is run. In other words, that task is performed by the CPU every time the user runs it. And so the more times the user runs it, the more time is dedicated to initializing these arrays. And because arrays can be quite lengthy, this can be rather time consuming, especially if you have to do it every single time you run your program. So why don't you just do it one time at compile time? Take that time to initialize your array once, and that way whenever you run it, you don't have to worry about it. You can just start executing assembly instructions that do something useful other than initializing an array, because it will have been done for you at compile time. So that's what we're going to learn now, how to initialize an array at compile time. Well, if you recall, we already know how to do it for a regular variable, like an integer, for example. Say we have an int I. The way we would initialize that at compile time, the way we would declare and initialize it at compile time is by using a label. So we make a label for I, and if it's an integer, we would do .int, which would get an integer's worth of space for us in our executable. And on a 32-bit machine, that'll give us 4 bytes of space for our integer. And following that, we would give whatever value we want to initialize it to. So a common thing is zeroing it out, clearing out your memory. A way we would do that is by putting the number 0. And so that is how we would initialize an integer, assuming that we want to clear out the integer to 0. Now, if we wanted to initialize our integer to another value other than 0, we'd replace that 0 with whatever value we want to give it, like -1 or 100, you name it, whatever you wanted your integer to take on initially. Now, we already know how to do what I've shown on the screen here. What we do not know how to do is an array. And so a question I'll ask you is, why would this not work for an array? And the answer is that this .int here converts to the size of an integer. And if we were going to initialize an array, we would have more than, like for an integer array, for example, we would have more than 4 bytes that we'd want to initialize. Maybe we want to initialize position 0 to something and position 1 of our array to something completely different. Using this syntax here, we would just initialize an integer's worth of space to 0 at I, and that's all we can do. Now, there's another assembler directive. Assembler directive, remember, is this .int here. Anything with a dot is an assembler directive. We have another one that's specifically designed for use with arrays, and that one is called the .fill assembler directive. So, let's say that we have an array A, and I've indicated that in our memory map here, and we're going to declare and initialize that array using the same general syntax that we did for just a plain integer. So we give a label for our array, and that matches where it is in memory. So let's say that our array, after we declare the label, that's going to be at address 100. Okay? Now what we want to do is initialize all this space here with some value depending on what's important to us in our program. Now we can only do 4 bytes with .int, so in comes .fill. With .fill, you can specify how many indices you want to be filled with the value, and you can also specify how many bytes each index of your array is. And so the best way to demonstrate this is simply with a few examples. Let's say I wanted to fill just one element of my array. So I want to fill A of 0, and let's give it the value -1. So we'll do all negative numbers for this example, just so you don't confuse them with addresses here. Let's say I want to put the number -1 at A0. Well, .fill takes 3 parameters to help us do that. The first parameter is how many indices, starting where you're at right now, that you want to fill this integer with. So in other words, how many positions in my integer array would I like to contain -1, starting where the .fill instruction is. Now, because I only want to put -1 into the 0th position of A, and that's it so far, we're going to put a 1 here. We want to fill one integer's space with the number -1, which we have yet to specify. So that's our first argument to .fill. The second one is the size of each element of the array. So remember, in assembly, we have to specify the size of our data types. There's no way to really tell assembly that I'm working with an integer or I'm working with a character. We as the programmers have to keep track of that. And so let's go back to this example of I up here. This .int has nothing to do with an integer really at runtime. all it's going to do is get an integers with a space for us. We can do whatever we want to with that space. This will return 4 bytes. And so if we wanted to, we could work with 4 characters at space I here. All this is doing is just a shortcut to get 4 bytes for us. So similarly with .fill, we've specified how many indices we want to have this value of -1, but we need to specify the size of each index of our array. Because assembly doesn't know otherwise. And so for us, that would be 4. Each element of our integer array is 4 bytes, and so we need to say so. And then finally, the last argument of .fill is going to be whatever you want to put in that position, or -1 in this case. So at the conclusion of this instruction, we will have a -1 at position 0. And so the way this works is, A is defined as address 100 here. Right after A, or right at address 100, the first thing we have is a .fill. And so starting at A, address 100, we are going to fill 1 times 4 bytes of space with the number -1. So -1 in binary is going to be contained in these 4 bytes of space here. Okay? Now, we've only done the 0th element of our array. Let's say that we want to set positions 1 and 2 both equal to the number -2. The way we would do that is just continue on with more .fills. And after I'm done with this instruction, I'll explain how this works from the beginning. So we have .fill. This time we want to fill 2 positions, 1 and 2. They're each 4 bytes apiece, and we want to put the number -2 at each of these. And so what that's going to do is, and I'll start at the beginning here, this is only going to happen one time at compile time, and it's going to start at the top and go to the bottom. So what happens again is A is going to be defined as a label. That's going to be given some address. Let's say it's address 100. So at address 100, first thing I want to do is fill 1 times 4 bytes. So fill 4 bytes with the number -1. Okay. At the conclusion of that, where that .fill left off, I want to fill another 2 positions, each 4 bytes apiece. So I want to start at address 104. And for 4 bytes, I want to put the number -2. So in those 4 bytes, I want to put the number -2. And I'll go here. Okay, now, because I have a 2 here, I'm going to fill another 4 bytes with the number -2. And that's going to be where the second 4 bytes, 104 to 107, left off, or in other words, we're going to start at 108 for that one and put -2. Now let's continue this example, and let's say that we want to fill position 3, so 0, 1, 2, 3. We want to fill position 3, 4, and 5 of our array, all with the number -3. The way we would do that is just right after this one, let's do another .fill. This time it's going to be 3 positions, each 4 bytes apiece, and we want to put the number -3 there. And so, again, the way this works is one time at compile time, this initialization will take place. And so only once are we going to go through all this code. And so we have to start at the top. So at the address of our label A, we're going to say that's 100. We're going to first fill 1 position of length 4 with the number -1. And so starting at address 100, we're going to put a -1, which will occupy these 4 bytes. At the conclusion of this fill instruction, and starting where it left off, so starting at address 1 times 4 is 104, we are going to this time fill 2 positions, each of 4 bytes, with the number -2. So the first one is going to start at 104, we're going to put -2 there. Then we're going to do the second of our 2 positions, which will start at address 108, with the number -2 as well. Now, where that instruction left off, we're going to do what comes on this line, and it's another .fill. So this time we're going to fill 3 positions, each 4 bytes apiece, because remember this is an integer array, and this time we're going to fill each of those 3 positions with the number -3. And so that means where the second .fill left off is where this one's going to start. So at address 10C, we're going to put the number -3. Same for address 110, and also for address 114. Okay, now let's just fill up the rest of our memory map here and do a couple more examples. Let's say that we wanted to fill the 0, 1, 2, 3, 4, 5, 6. Let's say we want to fill A of 6 with the number, let's say we want to put the number 0 there. So the way we would do that is simply with a dot fill, and this time we're only doing one position. So we're going to have a 1 again as the first argument. It's still an integer array that hasn't changed and should never change, so that's a 4. And then after that is the value we want to initialize it to. It's a 0 in this case. And so we got to start at the beginning again. This will only happen once at compile time. A is given an address. Let's say that for sake of argument, it's address 100. Starting at address 100 is going to be whatever comes here. It's a dot fill, so I'm going to fill one element of length 4 with the number -1. After that's done, at address 1 times whatever this is, 1 times 4, it's where I'm going to start. I'm going to fill 2 positions with the number -2, so -2 and -2. And from where that started, I'm going to start my next instruction here. So at 2 times 4 and 1 times 4, so that's 8 and 12. So starting at C, I'm going to do this third dot fill. It's going to fill the next 3 positions with the number -3. Each position is 4 bytes. So I have -3, -3, -3. And then we're going to start in our next position here at this much space beyond where this dot fill started. That's another 12 bytes, so we're going to start at address 118. Now, that is where we were going to do 1 byte of space, or sorry, 1 element of length 4. So only bytes 118 to 11b through 11b are we going to write the number 0. Okay, and that's where we're going to stop. Now, let's do another dot fill in this very last one just to fill up the memory map. So we want to do a dot fill of 1 to get this very last element. It's still an integer, and let's give it the number 10. So A is going to be defined again at compile time. That label is going to have an address. At that address, we're going to put -1 in the first 4 bytes right here, and the 2 bytes fall in the 2 positions following the first one here. So in other words, 0 is accounted for here. Then we have 1 and 2 right here. Each of those is 4 bytes, and we're going to put -2 there, and then likewise -3 in these positions. After that, we have a 0 in just this one position here. That's one position of length 4. So bytes 118 to 11b will have 0 in there. And then finally, after that, we have another dot fill, 1 times 4 bytes, which is one position of our integer array. Set that to 10. And that is how you can use dot fill to initialize an array. And so notice what we did in this case. We initialized different positions to different values. If instead you wanted to, and a common example would be to zero out the entire array, you could simply have so this array we did was a 0, 1, or 1, 2, 3, 4, 5, 6, 7, 8. It was 8 positions long. We could have done a dot fill 8, 4, 0. And that would have filled 8 positions, 4 bytes apiece, with the number 0. A 0 here, 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 and here. But a more powerful use case of dot fill would be to do something like this, where you initialize different elements of your array to different values, and so that's why I chose to give you this example instead. Now, one thing to notice is that every subsequent dot fill picks up with the first one left off. So this very first dot fill, because there's nothing but the label A before it, it's going to start at the label A, and the label A is address 100. So at address 100, it's going to put it, whatever its value is, in a total of 4 bytes. That means the second dot fill is going to pick up at 1 times 4 bytes after the first dot fill, or at address 104. So we go from 100 to 104. We're filling 8 bytes, so the third dot fill is going to start at address 10C. That one's filling 12 bytes, so 12 bytes from 1C, or 10C, is where the next instruction, which is a dot fill here, is going to take place. So that one's going to start at 4, 8, 12, which is 118. And then, because this one's only 4 bytes, the next instruction, which is a dot fill, is going to start at 4 from there, which is 11C. Now you can imagine if we had another integer underneath this array A or another global variable, we could move, well, that didn't work out. Well, I was going to try and move this memory map up, but what we could do is we could extend our memory map. And so we'd have another position here, and this goes on, this is continuous, it keeps going on in memory. This would be 1, 2, 0, and let's say that we made a variable, another one that we wanted to initialize at compile time. Let's say we had B after this A, and let's just say it's an integer because I only have enough space in my map here for another 4 bytes. And so for an integer, we could use the .int that we know already, but I mean you could even use a .fill to initialize an integer. There's no reason that we have to use this for an integer here. We can just use a .fill and say that we want to fill one element of length 4 with a certain value. And so we can do that as follows. So wherever B is, .fill one element of length 4, and we can initialize that to whatever we want. So let's just say 0. And so that means in our memory map, wherever B is defined, and that's typically, unless you have optimization going on, that's typically going to be wherever A left off. Now the way to tell where B would be is to take the starting address of A, which you can tell by our memory map here is address 100, and then adding the number of bytes that we're filling. So we're filling 1 times 4 is 4, plus 2 times 4 is another 8, so that's 12, plus another 3 times 4, or 12 to that, so we're skipping a total of 24 bytes so far. And then we are going to add another byte, so that makes 28, and add another one, and that makes 32. And so 32 decimal, convert that to hex, then it'll take us from address 100 all the way down to address 120 here. And look, that's right where I put B. And so if B is at address 120, we're going to do another .fill of one position only of 4 bytes in length to the value 0, which will look like this. So on that note, that concludes this example. The big thing to take away here is of how in general global variables can be declared and initialized and what they look like in memory. Now in reality you aren't guaranteed to have B located right after A here, but this just shows you how you can use assembler directives to declare and initialize space and how you can do more than one of these in a row. And by the way, this .int up here, for those of you who just want to look at this and try and map it out later, we never actually used this in our memory map, so ignore that up there. That was just an example of what we have been doing previously.